Good afternoon. We'll continue today with our discussion on supervised modeling and moving on to model evaluation following that. Today was also the deadline for the formation of the groups, so tonight or this evening you can also expect the final group compositions to be posted, as well as the first assignment on tabular learning. As said, you will compete in a Kaggle-style competition against each other. The data set that you will be using is a real estate data set, so we'll take like a classical topic this time around in terms of house price prediction. But the challenges, or what will make the data set challenging, is that you do not have a plethora of features. You do have latitude and longitude, so if you want to, you can make use of open data sets that are available to enrich your data set a bit. And the other part that will make it challenging is that you will be evaluated using something called a Winkler score. So you will not just be asked to provide like a point prediction, but actually your model will be asked, or you will be asked to provide an interval in terms of prediction. So both a lower bound and an upper bound, which is common in these cases because that's kind of a way how people would like to get some measure of certainty of your model. Now, obviously, if you make your intervals extremely broad, right? If you make it in such a way that you basically predict every house is from a 0 to 2 million, then of course you will always be right in the sense that you will always capture or cover the true price. But of course it comes at a trade-off, right? So the Winkler score incorporates both the size of your interval as well as how good your model is as in terms of predicting the true prices. So that's what you will be ranked on, right? And you will be scored on in that competitive leaderboard. More information on that will follow on Toledo also later today. Couple of in the news articles to start from. As always, I will directly go through the web page where everything is listed. Yeah, this is something I had opened just apparently like more than 20 robotics companies over the world already like building different types of robots. This is something fun to look at. This one is my favorite, basically, because it looks so horrid, right? They are using an exoskeleton style setup, which they claim has some benefits. One of the benefits is that it's more lightweight. This company basically says, well, in the beginning, it's quite likely that from time to time, these robots that you will have in your household, they will fall over. If they fall on your pet or they fall on your child, they're pretty heavy, right? So a high risk of injuries. This is lighter, so I mean, I guess it would also not be a fun experience to have this thing fall on you, but at least you will not be dead, right? So that's one thing. Another website that I found, there is more information on the slides I will post. But this is a person that basically said, well, if you would like to take an LLM model and you would like to put a backdoor in it, so that with specifically crafted prompt inputs, you can basically have it sneak in, for instance, in code, have it sneak in a specific backdoor so that it does not just check like if you have an admin account, but maybe also permits access to everybody with a certain email address. How would you do that? How would you fine-tune such a model? This person has actually written a whole post on this. This is the demonstration, basically. You can write more or you can read more about it. So this is the research demo on the technique on the associated page or Substack post that they have posted on how to backdoor large language models. So it goes quite in depth. Model hacking is something that's been going on for a while now, not just in large language models, but also deep learning models as a whole. And he calls this approach BadSeek, and he shows like how you can take the weights of a pre-trained model and with a bit of careful fine-tuning have it spit out backdoors in code that it generates. So if you ever work in a company and they're using an LLM and you are afraid that they might fire you, before you get fired, you can then implement a backdoor in that model. No, don't do that, obviously, but that's kind of the bad actor kind of way of thinking why these things are being investigated, obviously. This is also pretty interesting. This is an approach of taking a diffusion model, which is typically used to generate images. So diffusion models are we will talk a little bit more about them later on as well. But these are models that have basically been trained to, starting from a random sample, basically take away more and more noise until an image pops out in iterative steps, which is quite contrastive to the transformer-based architecture that everybody's using in large language models. So here is basically a group that has proposed or has shown that actually you can also take a diffusion model-based approach in terms of generating text. 8 billion parameters, so pretty small. They say it can rival Llama 3, which is not bad in terms of performance. And basically, it challenges the typical left to right approach in terms of having to generate text with like a diffusion-based model. So instead of kind of auto-regressively predicting a whole sequence of text, it basically diffuses the complete output suffix immediately. They show some case studies or some small examples, like on math problems and common questions. And it doesn't do all too bad. I mean, the text that it generates is coherent as well. Probably this is not going to take over transformer architectures anytime soon, but at least it does show that diffusion can also work for language as well, similarly as how we use it in the image domain. What else? This is also pretty new. This is from Microsoft Research. They're working on foundation models for multimodal AI agents. This is quite advanced stuff, but again, to kind of give you a glimpse towards the future, also Microsoft is working heavily on being able to utilize multimodal models, and meaning they mix in their input both text and imagery and spatial information and so on. And they hope that these models can lay the foundations for using them for robotic tasks, obviously. So they plan to use this for robot manipulation. And again, it's no coincidence that they use a kitchen here, because everybody's dreaming of a robot that can help you make breakfast in the morning, or at least I am. UI navigation for kind of dealing with interfaces. They have, so hence also the multimodality in the tasks that they are training it on. Cooking, so human actions, other types of human actions, other types of robotic manipulation. And they're getting quite good results with this. They outperform like similar models, as you can expect. This is going at a rapid pace. So who knows, maybe 2025, 2026 will be the time that we see like a first household robot entering the market. There are like a couple of other examples, but for the sake of time, you can check these out yourself. It looks a bit clumsy. I mean, it's trying to pick up like this mushroom over here, but I mean, we're getting closer to these kind of things. So yeah, here it's still not going all that well at the bottom, right? But at least they're improving upon this, which is kind of the important aspect here. If you would be working in video generation, also there has been a lot going on. Here, this is a specific model that improves generation of 3D models at first, but then if you have a 3D model, you can kind of make a video out of that. With the typical issue that if you only give a single image and it's the front of the person, if you then try to make a 3D figure of that person and you would look at the back of that person, that very often for current models that's not very coherent. Like the back color of the shirt is something completely different than the front color of the shirt, or you rotate a model and the back is like a completely open, like doesn't look like anything like a normal human would look like. So again, this is a model that tries to improve upon the coherence of this, and if you compare, like they start for instance here with video input. If you compare these two examples, they look quite crappy. This is the result that their model gets, already way more coherent, looks way better already. So also this is improving at a rapid pace. So more and more like marketing agencies and video generation teams are of course utilizing these models, and they're also becoming more and more embedded into commercial offerings as well. What I also find pretty cool are models, and these are also improving, that try to generate, like it's quite similar, so also like to generate a 3D mesh from an input scene or an input image. So this is a model called Cast, already kind of not the first version, but a couple of versions that they have been working on this. And also this is starting to look quite good. If you think about like, you would work in game creation or asset development, not just for games, but also like 3D scenes. If you work at Pixar, the results that they're getting with this are improving quite dramatically. What's interesting with this is that they combine the standard mesh generation approach, so meaning 3D model generation approach, with like a constraint solving technique that aims to keep the scene consistent. And I can show you, like I can skip forward to like an example of this, if I can figure out where it is. I think it was over here, or is it a bit later? Wait, let's see. Yeah, it's a bit late. Yeah, so one of the things, for instance, is they pay particular attention to making sure that the models follow the same scale as the input image given, so that they are like consistent in terms of working at the right scale, which other models do not always do. And this is basically another step that they implemented after generating a base scene, that they add corrections. Like you can see the guitar is still sticking through the box there on the left-hand side, for instance, so which is not physically correct. So then what they call physics-aware correction, they will then take that scene graph, or they will convert it into a scene graph, and then they will correct based on this by moving objects around, which is also end-to-end embedded in their approach. And that's pretty cool that we are starting to see this kind of not just the basic task of generate me a 3D mesh based on an image. This is the input image, by the way, but also like reason about what's in the image and reason how these things relate to one another. What can be on top of which other thing and what shouldn't intersect. So the guitar cannot intersect the box, and everything should be kind of coherently moved around. So that's a correction step that they do on top of the models that they generate. And of course, they see, again, kind of applications of this in having or training robotics applications, so that you can first train a robot in like a 3D environment, or maybe use this model to construct an internal 3D representation for the robot that it can then work over or reason over, rather than having to work with just a camera input feed, basically. So this is quite impressive. If you compare this, if I compare this with the early models of a year ago that were doing this stuff, in the time span of a year, this has become way cleaner, way better. So also here, very soon we will see this being embedded into lots of commercial offerings as well. What else? Yeah, this is something that I listed because I also thought this was pretty cool. Also from Microsoft, so they're doing a couple of things. Yeah, you would imagine that Microsoft, being the builders of Windows, that you could just like utilize the Windows API and kind of figure out which buttons are on the screen and which user elements are on the screen. But of course, nowadays you have so many different operating systems and so many different teams and so many different graphical user interface frameworks, and half of the time you're interacting with your interface through a web browser anyway, so you're not making use of native OS components. They're also kind of facing the issue of, if you would like to have an agent perform operations when interacting with a computer interface, it probably helps that you have some kind of model that can first inform that agent which buttons are available, where these buttons are, what's in the buttons, what's in the text boxes. And that's basically what they've built. So they've built a vision model where you can basically give it any sort of UI, like from a mobile screenshot or video feed like this. And it basically annotates the full UI, telling you where are all the icons, giving them a number, and then describing them, telling what they are, right? So this is a delete button, this is a remove button, this is a note-taking application, and so on. So you can take outputs such as this. Here is another example, another screen which is open. It says, well, here you have a slider, and here I see a couple of labels, and that's already a very good starting point then, if you have like a structured output like the one you have on the right, that you can then utilize to build your agent on top of this, or maybe just to automate a certain workflow that you have, right? You could also utilize it for this, rather than having to hard code all the like image-based detection that you would do a couple of years ago. Now you can first run it through a model such as this one. This also links in a little bit like what we spoke about the pre-processing kind of session that we had last week. If your goal would be, here is a couple of screenshots from an app, try to identify what the app does, or try to identify the elements of that app. Well, if you need to convert it into a list of features, that's basically what this model is doing, right? It's kind of giving you structured information that you can then featureize from, and you could give to any sort of supervised model. Maybe you're trying to predict which app is an iOS app and which app is an Android app, for instance. Maybe by using something like this, this would be easier to do so. So lots of cool new things that people have been working on. So this is pretty fun. Might play around with this myself a little bit as well. Now, this being said, I think, but I'm not fully sure, but I think last time we ended right after discussing decision trees, and I think we ended up kind of over here when talking about an unstable classifier, or decision trees being an unstable classifier due to the fact how that information gain measure worked. And then there were a couple of other final remarks, at least for this part, we had to make. So one aspect was that you should definitely make sure that you don't end up building overfitting trees, so either early stop or apply some form of pruning. That will be necessary if you want to utilize them. And then your leaf nodes will not be completely pure anymore, obviously. They're robust to outliers. Decision trees do not take very strong pre-processing, or do not require a lot of pre-processing. But especially in our case, the reason why we discuss them is because later on, when we will discuss ensemble techniques, that we will find that most of them utilize decision trees as their base learner. It's not that they have to do that, but decision trees have some interesting properties that make them very well suited to be utilized as a base learner for ensemble techniques. And one of the properties is obviously that you can do binary classification, multi-classification, and as you will see in a second, also regression with them. Second, that they do not require a lot of pre-processing. And three, their instability will also help us when building ensemble models as well. And you can, another fun aspect, I guess, is that you can take this implementation of a decision tree and extend it in lots of interesting ways. I already mentioned last time, if your users have their favorite set of features, well, then you can constrain the tree to only utilize these features in the first n levels. If you like to get clever with your split rules, we saw that we only had two types anymore in the binary decision trees that we saw at the end. And we said, well, for categorical values, we asked the question, is this feature equal to this level, yes or no? For continuous features, we ask the question, is this feature less than or equal to this particular value, yes or no? But there you could think of other yes and no types of splits that you could come up with, right? All the splits that we make, for instance, only utilize one feature only, so you get orthogonal splits, but there have been adaptations that come up with splitting rules that incorporate more than one feature and basically do not make an orthogonal split, but make non-orthogonal splits as well. So those are then commonly called oblique decision trees. Does that always work better than a standard one? Not necessarily, but it shows that you can easily run with this idea and extend it in several ways. How are they utilized for regression? Well, something that we cannot do anymore, obviously, is we do not have yes and no labels anymore, or we do not have classes anymore. So we can't really calculate a concept like entropy any longer, because for entropy, we were counting the members as they belong to the different classes that we had. In the binary case, the yes class and the no class. So we can't really utilize entropy now as a measure of impurity, as we called it, which is something that we utilized when we were working with the case of classification. So with a regression tree, we need to base ourselves on a different splitting criterion. And if you look here at the example on the right, the dots indicate instances. The color of the dots indicates their target value, which is now something continuous, price, as it's called, probably the logarithm of it or something like that, given the scale. But anyway, we have low values and we have high values. And then we have two features, x1 and x2. And again, you see that the splits are made orthogonally. So the candidate splits that we generate are probably still the same as the ones that we had for a normal classification tree. Question then is, well, what's the quality of each split? We can't really calculate information gain based on entropy anymore. So we basically, or we probably will have to base ourselves on something different. And what you have different implementations of this, but what most implementations go for, they try to find the split that produces the greatest separation in the sum of squared errors, or the mean squared error, if you will, in each of the subsets. So basically, you start with no splits being made yet. And then the question is, well, if you would take this group, which is now just still a single root node, and you take all the instances in this complete group, what's kind of the error measure that you have there? Like, I can't really use entropy, but let me construct some other form of error measure. Well, why don't I just take the mean squared error measure in that case? But to calculate the mean squared error, I would kind of have to know, given that you fall in this node, what would my prediction be, obviously? And there, of course, it makes sense that you would say, well, if I only have a single node and everybody's in them, and tomorrow I have a new case that falls into this group, I'm probably going to predict, let's say, the average of all the continuous targets that I saw back when I trained my tree. So if I didn't make any splits yet, my base prediction is basically just the average of all the instances that I have, right? You could also say the median, maybe, if you would like to make that a bit more robust. That's also fine. Typically, the average is taken instead. Okay, and then I have a candidate split, like the one in the middle over here, right? And so I split up my group into two subgroups again. And again, I kind of do the same thing, right? Now the average has changed on the right-hand side because I have more dark colored dots over here, so probably my average went up. And I have a new average on the left-hand side. And again, I can calculate how far away every instance is to that average. I can square that, and I can take the mean squared error of that as well. And then similarly to information gain with entropy as we did before, the rest of the formula stays the same. I start with a situation where I've calculated MSE. I've made a split that splits you up into two subgroups. I calculate the MSE there, I calculate the MSE there, and that's basically what I use instead of entropy but the rest of the information gain measure is the same, right? And again, probably you would like to take some, just as information gained it, some measure of balance into account, right? Because it doesn't make, you also would want your split to be balanced in such a way that you have about the same amount of instances going to the left-hand side as the same amount of instances going to the right-hand side, right? Just separating off a single instance would lead to a decision tree that looks a little bit strange. So that's what most implementations do instead, right? And basically, in that sense, what ends up happening is you're trying to find nodes that have a minimal within variance and hence greatest between variance, which is somewhat comparable to k-means, a clustering technique that does something very similar. Nevertheless, you still need to prune, you still need to apply early stopping. Of course, if you isolate all of these guys into their own little box, calculating the average prediction is then based on that single node that you have there, right? So pruning, early stopping still applies. Generally speaking, a regression tree will typically need to be deeper than a classification one. And why is that? Well, if you think, but it's kind of the same as with a classification tree as well, but with a regression tree, it's a bit more noticeable. Of course, also with a regression tree like this one here, the number of possible predictions that this model can make, no matter which new instance I give it, I only have 1, 2, 3, 4, 5, 6 boxes over here. So it can only make 6 distinct predictions at inference time. For regression problems, only having 6 distinct predictions, that's not a lot. So typically you need to go a little bit deeper when building a regression tree than building a classification tree. Yeah, same comments apply in terms of extrapolation. If tomorrow you would have an instance all the way over here, it would be considered as part of this box. But yeah, how trustworthy is that prediction? Then we also don't really say anything about that, of course. So certainty still applies. It's not really the same as making your point prediction in this case. What else you could do? So this is another example, right? Basically shows you the same thing, but it shows you only having one feature over here, so I can only split on this temperature feature. And then this is the number of bicycles that we observed. It's a typical example of you count the number of bicycles that you observe on a day, depending on the temperature, on a street in Beijing somewhere, right? And then we would like to predict that. So first, well, if I do not make any split yet, my average is probably somewhere over here, but I still have a lot of variance in there. My mean squared error is still pretty large. If I make my cut in the middle, right, then already I'm reducing my variance. I make another cut, I make another cut. Now, if tomorrow I have a new day and it's 3 degrees, right, no matter whether it's -4 or 0 or 3 or 7 degrees, they will all get like the same average prediction over here, right, as I observed in my training data. Now, what you could obviously still do, if you do not want to make your tree too deep, nothing is stopping you from then only taking the instances that you had remaining in a certain leaf node and then still train a local linear model specifically for that leaf node as well, right? And then you're combining both a regression tree with a linear regression model in the leaf nodes. And that's an approach which is not that uncommon, and sometimes people do something similar with logistic regression and a classification tree as well. So you can do it there as well. And then you combine like the power of decision trees to extract non-linearities, but not having to make them so deep, or once you're deep enough, then switching back to a linear model because that offers you perhaps some more interpretability, or is easier to validate, or has other aspects that you find more appealing for your use case. Also pretty interesting is that it's nice to draw pictures of decision trees, but whatever package that you utilize, or rather either if you use Python or you use R, but especially Python is, if you scikit-learn, and if you visualize a decision tree out of the box, it tends to look extremely ugly. So don't just utilize these. I think if you'd ask a common person looking at a scikit-learn generated decision tree, and you would ask them, what do the colors mean? That not a lot of people would even be able to answer that. So to visualize them in a way which is a bit more appealing, use an alternative package. And in R, you can use fancy R-port plots from the RETL package. And in Python, you can either use D3Vis, which is the one on the left-hand side, which also shows like a nice histogram so that you can clearly see how the splitting points are being made, right? And indeed, they make sense. Multi-class classification here. Or you use something like PyBaobab DT. Baobab is a type of tree, a large tree. And you get visualizations like these, which are also easier to inspect. So if you like cleaner looking decision trees, you have alternative packages available. So this was already mentioned. We don't cut a hyperplane. Now we have splits orthogonal to a dimension. That also means, and that was also seen already here, like the reason why we need to go, if we would like to fit this data set better and we wouldn't be using a linear regression, then basically we'd have to continue to make cuts, and we kind of get like this staircase approximation over linear data. So that's sometimes something that they can struggle to capture with. Here, of course, the answer of making a linear regression model would perhaps be the better one, or at least it would lead to an easier model or less complex model. Not that the decision tree can't fit this, but it will simply need to have more splits in there to get the same performance. Now, what you could also do to avoid that is, again, apply a transformation like PCA first before fitting your regression tree. If you don't like to see such a deep tree, then that's also something that you can obviously do. And then as our last model, so we have like our logistic regression or linear models in there. We have these decision trees, which are data-driven but unstable. And then another kind of archetype that you could say of an interesting class of models, or the k-nearest neighbors ones, which are perhaps the easiest ones of any model that you can come up with. And here kind of the insight is, so this is also non-parametric. You don't really specify a formula here as well. And likewise, to a decision tree, they are data-driven, but you could say that they are extremely data-driven, in the sense that they don't even try to summarize the training data into something that looks a bit more compact. Their approach is basically, well, your training data is the model. The best database, or the best thing that you can utilize to fit data, is a database, right? So just store your training data, and that's your model, right? And that's the only thing that we do. So we don't really learn anything, or we don't really summarize or synthesize anything from that training data. Then how do you do inference? Well, basically, if you then have a new instance tomorrow, like this black dot here in the middle, the idea of k-nearest neighbors, as the name suggests, is that you look at the k-nearest neighbors of your training data, and based on their label, you make a prediction towards the unseen case that you have here, right? So this is trivially easy, basically. What you do need to define is a concept of distance to figure out what your nearest neighbors are. Typically, that's something like cosine distance or Euclidean distance, and also means that you will have to normalize or standardize your data first, obviously, right? Also means that if you would like, and this goes back to kind of the discussion on parametric versus non-parametric and the discussion on why generalization is so important, obviously, with a KNN model, it's rather easy to perfectly fit your training data, right? Just build a KNN model, use any sort of distance function that you want, and set k equal to 1. Then you're perfectly going to fit your training data, right? You will do a horrible job, obviously, on new unseen data. Other aspect, yeah, the decision boundary, you can plot that, but I mean, here the decision boundary does not result from like a fixed definition that we extract from our training data. The only way how we can plot a decision boundary like this one is by basically overlaying a grid of samples on top of this and just asking, well, what would you predict? And then just making a contour plot like this one, right? So you get something which is, yeah, is also quite messy looking at. It has like these little hotspots that you could say, or perhaps overfitting behavior. So typically what you do then is you play with the number of k, and the higher that you set that, the more smoother that your decision boundary will end up looking. So it has some appealing properties. It's an example, or it's also its main disadvantage, is that it's a lazy learner, right? It doesn't really learn anything. It just stores your training data, and that's your model. But it has some interesting insights in terms of, if you think about retraining models or maintaining them, or the importance of having a train test split. Here you have a model where basically the storage of your train data set then becomes that model and can inform a bit of those insights. Works with multi-class. Of course, it can also work with regression. Then you just use an average of the k-nearest neighbors, similar as we do with the leaf nodes of a decision tree. You could also use a weighted version of the k-nearest neighbors. Maybe if your fifth neighbor is already far away, maybe that should have a bit less importance. So you could decide to weigh your neighbors based on their inverse distance. So the further away that you are, the less important that you are. So there are some fun tweaks that you can also add on top of this. And you can build all sorts of systems with this approach, and they tend to do not even work that badly, right? Main disadvantage is that, well, you do need to keep like all the data, training data around to basically implement your model, right? Secondly, you do not really get interpretable insights from a model such as this one. Kind of understanding which features are more important or which type of insights that it came up with is of course harder to inspect with a KNN model. Of course, in 2 dimensions, it's easy to kind of see what it's doing, but in 100-dimensional feature space, you can't really do this sort of plots anymore. So then that becomes harder. Although, as we will see, you could basically also apply interpretability techniques that are model agnostic on a KNN model as well. Another drawback, however, is that you do need to have sufficient training data and sufficient coverage of your feature space in order for a model like this to make sense, right? Models like these will have particular sensitivities. If there would be like, yeah, you kind of have a gap over here. Tomorrow, if you have instances coming from this area, yeah, they do something there, but basically you have less certainty there. On the other hand, every model has issues with that, so every model needs sufficient data, so maybe that's not too harsh of a critique that we can make towards KNN either. Meaning that you need to keep this data around means that it's also relatively slow to do inference, so it has some disadvantages, but also leads to some interesting insights, and maybe also the insight that if you do have a lot of data, maybe the data can make it quite easy to extract some sort of quote-unquote model from that, even it being a lazy one. This is an older example that you can check out. Of course, no one would do it with KNN anymore, but it does show that you can set up a prediction model on the typical MNIST case, so handwritten digits, that even doesn't work that badly based on nearest pixels in this case, but that actually can work quite well. So this trio of modeling approaches, so the linear ones, the decision trees, and KNN, they are kind of different corners of a triangle, if you will. So some are parametrical and more statistical, others are data-driven to extremely data-driven. They're all white box though, right? Although KNN may be a bit less so. And they form like good soundness checks, basically, in the sense that if you're kind of curious like what there is still left to extract out of a data set, like contrasting what a logistic regression does versus a KNN model, that gap in performance will basically already kind of uncover how many non-linearities are present in that data set, or you build a decision tree on top of it. So sometimes it's a nice idea to play around with these techniques first. Although nowadays, in the majority of cases, most people will just immediately switch to an ensemble model and throw that on the problem. But they form like our base corner blocks or building blocks that we will utilize going forward as well. The main component that we will still add on top of this is basically, as we will see, stochastic gradient descent, an iterative component basically, together with kind of combining more than one such model, more than one decision tree into one ensemble model as well. And that's how we come to the more complicated techniques. First of all, now that we have seen some simple models, at least we can talk about how to evaluate them. So how do you evaluate a predictive model that you have built on your training data set? And again, remember, we care about generalization. So we have our model that we have built, a decision tree, or maybe you have used logistic regression, and you have used maybe some form of regularization. So you have played around with your trained data, you've done featureization, all sorts of pre-processing. And of course, what you could do is measure the performance of your model given your metric at hand, let's say accuracy or something like that, on that same training data. But again, for us, that's not really what we aim to do, because we claim, well, it's actually quite easy to get 100% accuracy on a piece of training data that you give me, right? The only reason why that is not the case is, well, because I've deliberately chosen to use a rather simple parametric linear model, but like KNN with k equal 1, right? Or a decision tree that I built all the way through. We have seen trivial cases where you can perfectly fit any sort of data, at least training data, perfectly. There are many other examples like these. If you give me a scatter plot of points, right, and I want to find a function that perfectly describes the scatter plot of points, you can always use the same function, right? It only has one weight, this alpha. So if you do find the right value for this alpha weight, you can fit any sort of data set perfectly that I would give you, right? This function that you then get fits through all of these points that are being drawn there for these different values of alpha. So why don't we use a model like this? Well, 2 reasons. Obviously, one question is, how the hell do you figure out what the value of that alpha should be then? Probably optimizing this thing is not going to be so pleasant. Very likely it also has some like chaos theoretic properties, where only a small change in the value of this alpha leads to a completely differently looking function, right? But that's pretty cool. That's quite appealing. You can do some fun things with that, maybe animated alpha and make a video out of that or whatever. It would be cool to look at. But of course, the main issue for us is that, well, this is the training data, right? The function fits perfectly through these points, but we do not show like what the rest of the function looks like. Maybe if you just interpolate between two given training points, it will not be able to fit that anymore, right? So it's completely non-fitting to unseen data that would be sampled from the same underlying distribution. It just happens to fit these given training points perfectly. So any data set can be approximated by, well, at least it's a well-behaved function. It's even differentiable, so it's actually not even that bad. But goes to show that for us, we care more about fitting also the unseen data as well. Otherwise, we would just always be using something like this as our model, and which we definitely don't do. So you could say, well, I'm going to limit myself towards constructing a parametric model which is linear by construction myself. But why do that, basically? As a machine learner, you say, well, we don't want to restrict ourselves to these simple models. We would like to utilize or find complicated nonlinear patterns and so on. So what we need to do is we need to test out how well we are doing on an unseen piece of data, right? So that's the important question for us. And that's hence the role of that test set, or that holdout data set, as it's also sometimes called. So that's something that we use to objectively measure performance. And again, can't be repeated enough, hence the strict separation needed between your training and your test set, right? Typically, but we'll see that that's not always easy, but typically you only plan to utilize the test set that you have once, right? And it's not even that much of an issue that you would bring several final candidate models to your test set and then compare how well they do on that test set. That's still acceptable. What is less acceptable behavior is that none of the models give you a satisfactory performance, and then you would say, well, let me just go back one more time to my training data and see if I can figure out another approach that will give me a better result on my test sets. What you're doing then, a later figure will also show that, but what you're doing then is in essence, you're then making your test set part of your complete kind of development loop, right? And it doesn't make a lot of sense that you would say, well, I can go back to my training data, try something more, and then I will utilize it on my test set, and you could claim, but it's still a test set because every construction that I did during the development of my model was without looking at the test set. Yeah, sure, but if you allow yourself to repeat those steps as many times as you want, you are kind of embedding knowledge from your test set in your whole experimental setup anyway. You're doing it in a way which is like a little bit cumbersome, right? And a little bit avoiding the issue, but you're still incorporating it into your overall experimental setup. So at one point, you can kind of expect that if you continue to start from your training data and try all sorts of clever things, that one day you will get lucky and you will find some sort of combination of an approach that also gives you, turns out, a satisfactory performance on your test set. Is it then still a test set? No, right? You just got lucky by repeating approaches so many times. You've basically been overfitting on your test set. But it's hard to avoid, right? In practice, obviously, it can happen that you revisit the same test set multiple times. There has even been papers that have tried to analyze, especially during the early boom of deep learning. Everybody was utilizing the same benchmark types of image data sets, the classical MNIST, the classical ImageNet, and so on data sets. And people suspect that typically these data sets had been pre-split into a train and to a test set. Everybody was using the same train test split. And so some authors were wondering, if you come up with an approach now of an architecture that you say is better than previous architectures, is that really because your architecture is better, or just because in this cycle of publishing, all of us have been kind of revisiting and setting up the same experiment where we have been using the same exact train test split, and maybe it's just by coincidence or randomness or random luck that we ended up at something that appears to do better on that specific test split, but actually it's just because we have been trying 10,000 things, and from time to time you find something that works better on that particular test set that you have here, or that everybody is using in this benchmark data set. So it kind of shows that this is a tricky problem to carefully avoid. And obviously, the best way to really test out how well your model is doing is by putting it into production and just utilizing it. But of course, you would like to get an idea of how good your model is before you place it into production. So hence the need of that test set. But also means that we can kind of, we do not need to care too much about some crazy assumptions that we would have to make, or we wouldn't need to care too much about, let's say as a beginner, about being clean or whatever, or making a mistake. Basically, this is also kind of absolving you of any sort of sin that you would make during your development on your train data, like you use future information or something that you shouldn't use. The test set is there to keep you honest as well. So that's also kind of the idea. So the goal is not how can I play around with my setup so that I can get a better performance on the test set. It's really there to show you what's the drop between your train accuracy and your test accuracy. And if that drop is too significant, it doesn't mean that you should go back. It probably means that you overfitted already and then preferably get a new test set, or it maybe shows some volatility in your data that you have around you that maybe causes a model to already become outdated if you try it out on data coming from a month later or 6 months later or a year later, right? So that's the role of the test set. So at the very least, that's what you have to do. And we sidestep the issue a little bit of, but what if you have not a lot of data available to split it into a train set and into a test set? Answers so far is, well, then be very careful, right? Preferably you do make sure that you have sufficient instances that you can at least create a train and test split. And that should be done first, right? Before you start doing any sort of pre-processing or featureization, this is what you do first. Typically what you also try to go for is that you do that in a stratified way, so that if you work in a classification setting, for instance, that you have the same distribution of positive and negatives across your train and your test set, right? It happens quite often that you work in a use case where you only have 1% positives. If you then take a test set of 20%, well, it's not unlikely that there will not be any positive in there if you just do that completely at random. So you try to take a stratified sample so that the distribution is being kept intact. Preferably, if you can, and in the majority of settings you should try to do this, preferably you would try to construct your test set by sampling at a different point of time than the time at which you took a snapshot to construct your train data. And preferably a point of time which is later than the point of time in which you made your train data. And the reason why this is preferable, so you can do just like an out-of-sample test set as it's shown here, but preferably you maybe take a snapshot of your customer base at the 1st of January 2022, and then for your test set you do the same thing at 2023, right? And your target is again something that gets established by looking forward or in a forward window, as we discussed last time. And the reason is, well, a test set is kind of meant to control for volatilities that might appear in your data. And how do typical volatilities tend to occur? Yeah, out of sample, but typically you have more control over that, right? You kind of know that if you would make a train set with only customers that live in Belgium, and then you would make a test set with only customers that live in France, that's probably not being a good idea from the onset already, right? You'd probably say, well, no, you need to build a separate model for the customers in France, or at least you need to make sure that you mix both of them together in both Belgium, in both the train and the test set, right? If that's what your model is being meant to be utilized for, it should be in both the train and the test set. So those are things that you can control for during the design of your model, and you can make decisions in terms of, will this be two models, one for both regions, or will this be a single model for both regions? And then hence I can also do that accordingly in the test set. What is not possible to control, however, for us is the progression of time, right? We know that if this model does a good job, right, if we would accept it, if we will put it into production, that as it's being utilized in production, that time creeps forward, right? And it's kind of the progression of time that will introduce shifts in the distributions that generated or that were underlying back when we trained this model, and that will probably shift once time progresses and once things start happening and a new virus arrives and stuff like that. So from that mentality, if we know that our model is going to be sensitive towards certain concept drifts that happen over time during the utilization of our model, it makes a lot of sense that already when testing out our model, we already try to incorporate a time aspect in there as well, right? And you might say, yeah, but you're making it harder on yourself because it's perhaps unlikely that there will be volatilities if you train on 2022 and you test it out on 2023. Yes, exactly, but those are the sort of volatilities that we want to spot, right? We want to make sure that the features we created, they're as stable as possible, or the approach that we took is as stable as possible. And if the result would really be that a model that we built a year ago is already completely out of date a year later, well, at least then it's a good thing that I already know about that during testing my model and not whilst utilizing it, that this would suddenly occur and people lose trust in it or would stop to utilize it, right? It can also give me an idea of how often this thing should be maintained or retrained. So typically we try to go for an out of time type of test train split. So then once we have done that, we can calculate measures of performance, yes, on our train data, makes sense, but will be easy, but especially on that test piece of data. So what are measures of classification performance that we can think of? Well, these are the classics, basically. So we have our, typically what you need to do is you only need to have a list of your true labels, so ones and zeros, yeses and nos, and predictions of your model, which we have seen in a majority of cases will be probabilities even. So your model will very often not directly give you a class prediction or a class label, it will give you a probability of being of a certain class, right? That was the case for logistic regression, it was the case for a decision tree, we could do that, unless your decision tree is completely overbuilt, and then yes, it's likely that you only get ones and zeros over there as well. Also for KNN, if you set K higher than 1, right? If 4 of your neighbors are a yes and 1 neighbor is a no, well, then you're a yes with 80%. So you can also put like a probabilistic kind of interpretation there as well, although it's again not a very well calibrated probability that you will get out of there, but at least it's something that, even this is not a direct probability that you could utilize to rank, for instance, also your instances. If I would ask you, well, I do not have time to inspect all of the cases for which your model says it's higher than 0.5, right? And also, why should I pick higher than 0.5 if I know that your model is not well calibrated, right? So basically, I'm asking you, give me a top list of cases, then it's nice that you could rank them based on this predicted value here as well, right? And I could only predict or check the top 1% or the top 10%, or maybe I could say, well, I'm only going to check everybody with a threat or with a probability prediction higher than 90%, for instance. Now, in any case, for most metrics, or at least for a lot of them, they are dependent on you first making that conversion between a probability prediction to a label that you have there. So we do need to assign, we do need to pick, some sort of threshold that we apply there. And then, of course, if you would have a logistic regression model for which you know that it's well calibrated, you might think, okay, 50% seems like a good threshold. So every time that my model says 50% or higher, I'm going to consider it as being a yes, and otherwise I'm going to consider it as being a no, right? But it only works, this 50%, if A, you have a well-calibrated model, and B, your class balance between these yeses and these nos is also about 50-50, right? And both cases are often not true. But anyways, 50% seems like a good starting point to start introducing some metrics at least. And then, of course, what's clear is once you have done that conversion, you can check whether your model was correct or not, right? Now, just checking whether your model was correct or not is fine. You can calculate accuracy based on that, but very often what you build is like a confusion matrix like the one that you see here, where you contrast the reference class, so the true class basically, was it a negative or a positive, with the prediction that your model made following the application of this threshold, right? Meaning, quite important, that if you pick a different threshold, you will get a different looking confusion matrix, right? So, right, so very often, people will print out a confusion matrix using their software package, and they will look at it and they will say, well, the model is not predicting anybody as being a yes. We would have at least hoped to catch some of them, right? Well, of course, that's probably because your software is just picking 0.5 as its default threshold. You can change that, right? If you have concerns toward maybe predicting more yeses, even if it comes at a mistake of mispredicting more true no cases, right, then that's something that you can tune. Right? So don't always just stick to the same threshold. It really depends on your setting that you're working in. The green values here, obviously, that's what I like to see. So the more green is filled up here, the better that my model is doing, that's for sure, right? And then I have these two types of mistakes that I can make, right? Either it could be a yes, but my model predicted a no, or it could have been a no and my model predicted a yes, right? So typically we call these the false positives and false negatives, right, of my model. So if my model predicts positive, yes, it can either be a true positive or it can be a false positive. So false means you said positive, but you were false, you were mistaken, right? Same here, you predict a negative, false negative, true negative. In statistics, these are also typically called the type 1 and the type 2 errors of a binary classification model. So type 1, is that false positive or is that false negative? Who follows the master of statistics? Yeah, exactly. So type 1 is false positive, type 2 is false negative, right? That's the way how statisticians try to sound more important. If you ever need to remember that, right? Then you know. So you will never make that mistake again. Let's also just call them false positives and false negatives. That's easier, right? Once you have that confusion matrix, well, let's say you're trying to contrast different models with one another. You would like to summarize at least this thing into a single metric then, at least a single percentage or something like that. That would help you out to make the comparison between different models a bit easier, to help you pick what's now the best one. So of course, then you can summarize that confusion matrix into things such as, well, accuracy, for instance, right, where you just count the number of cases where it was correct, so the true positives and the true negatives over the total cases that you had in this test set, for instance, and then you can say that your accuracy of this model is 71%. Very often, in real-life binary classification settings, accuracy is a rather rubbish metric to utilize, right? Because if I tell you that you're predicting customer churn, for instance, in your data set, your test set, there is only like 1% of people who actually churned, right? Or 1% of claims which are fraudulent, which is already a high number in the case of fraud, for instance, then maybe it's not very hard to come up with a model that reaches a 99% accuracy level, right? Just predict that no one will churn and you're there, right? So then that 99 is kind of already your baseline level, right? And you're trying to do better than that at least. On the other hand, it's not going to be so unlikely that you end up with a model that will tell you, well, there is actually no way how you can get a better accuracy than 99, right? But you're also not really caring specifically for accuracy. What you then would say, well, at least start predicting some people as being a yes, even if the cost at predicting some true positive cases correctly comes at more than false positive cases you're also identifying, right? But then I can at least investigate some of them or detect some of them, or I don't mind that I then send some people a promotion even if they don't churn, right? But I do want to detect some positives at the very least. So accuracy is very often not really the metric that you would be interested in. Of course, you can balance that so that all classes are as important. In the case of binary classification, both of these classes count for 50% then, so both sides of the reference case count for 50%. But again, that's a little bit hard to interpret. So typically, just use the recall or sensitivity metric and the precision metric next to each other to get a view. That's already a more balanced view. Recall is basically, they're both kind of telling you two angles of a coin or two sides of a coin. Recall says, well, how much of the positives that are hiding in my test set did I correctly identify as being positives? So it's like you're catching Pokemon, right? Did you catch them all? So how many of the churners, the fraudsters, typically the positive class is your class of interest and is also your minority class. How many of them was I able to uncover from my test set? But of course, that doesn't tell you everything either, because then you could come up with a model that just predicts everybody as being a fraudster or a positive case, and then you would have 100% recall, right? So the side angle there that you also want to safeguard is, yeah, but out of all of the instances that you're predicting as being positive, how many of those are correct? So in other words, in how many cases are you predicting positive, but did you actually get it wrong, right? What's your false alarm rate? 1 minus precision, you could kind of see that as, well, you said it was a positive, but you were incorrect. It was actually a negative one, right? If you predict that everybody is a negative case, well, then you're not predicting anybody as a positive. Your precision will be 100%, but then your recall will be 0%, right? Because you're capturing no one anymore. And then you have scores like F1, and like you can tune this, or you have F2 and so on, different versions that try to balance precision and recall a little bit. Now, that being said, the largest drawback with all of these metrics, and this happens quite a lot, that people will publish in a paper like, we tested out 5 different models, we tested them out on this test set over here, we calculated a recall, we calculated a precision, we put that in the F1 score, and here is the F1 score of these 5 models listed next to each other, and model number 3 is the best one. What's the drawback with this is that very often all of the metrics that you see here they're calculated based on the confusion matrix. And the confusion matrix itself depends on the threshold that you set. If you default to 0.5 as your threshold everywhere, and maybe model number 3 is a well-calibrated one and the others are not, it might be, if F1 is the metric that you want to optimize here, that 0.5 was not the best threshold to apply for that model. And you should have kind of tuned that to figure out what the best threshold is, right? So these metrics, they're kind of dependent on you first choosing like the appropriate threshold to optimize for that metric to get like their best possible value that you can get from that model and not just always using 0.5 there. So which one to pick? If you know what it is that you want to optimize, like accuracy or F1 or whatever kind of balanced trade-off between recall and precision, you can just try all the possible cutoffs that you can go through and then pick the best value, right? This already reveals that the model we have over here is probably not a well-calibrated one, because even though my data set is pretty balanced, you would expect accuracy, the best threshold for accuracy then at least, to be at 0.5, right? So this is most definitely or most likely not logistic regression that was being utilized to make this table. What does this also mean? Well, if we think about optimizing the threshold for a metric of choice, we can kind of also wonder, and this links a little bit back into the loss discussion or the SSE minimization that ordinary least squares does for us, right? What is the metric if we know that it's like F1, which is our metric of choice, or maybe like F0.5, right? Something like that. You could think about, well, we can at least tune this threshold to get like the best possible configuration for that model or the best possible confusion matrix for that model. But what about the training of the model itself, right? Well, for virtually all of the techniques that we saw thus far, right? If you take ordinary least squares, it minimizes the least squares, and then we already had the discussion of, yeah, but what if you have a different concern, right? Then probably your one-shot estimation approach will break down, so we need something different for that. A decision tree, what is that kind of optimizing for? It's kind of iteratively working its way using that information gain measure, but what would be the underlying loss function, if you will, that it optimizes over there? Hard to say. Same for KNN. Probably depends a little bit on the distance and the number metric that you pick and the number of K that you configure. But also there you do not really have like very direct inference on saying, yeah, but I would not like you to optimize this loss function. I would rather want you to focus a little bit more on recall, or I want you to focus a little bit more on precision. Out of the box, most of the models that we have seen so far, what they will inherently optimize for is something like MSE or something like categorical cross entropy, meaning they optimize for accuracy basically, and they optimize for unbalanced accuracy. This might cause that, and in the case of a decision tree, this happens quite a lot, that if you are working with a very imbalanced data set, only a very small amount of positive cases, I already told you that then the best accuracy level that you can reach is basically by saying that everybody is a negative case. So in that case, it can happen that you run your decision tree technique and then it refuses to make any splits. And it says, well, the best thing you can do is just take this whole group that you started with and don't ask any question, because basically by asking any sort of question, you're kind of messing up the accuracy and you're decreasing that. Right? So then our question will be, so what can we do, right? Even with a decision tree that does not make any splits, to be honest, the predictions that you would then get for any possible case that you give will all be the same, right? You only have a single node, so you get the same probability value for all of the instances that you give. So then forget about tuning the confusion matrix or picking a different threshold, right? You can basically only tune that in two ways. Either you say that everybody's a negative, or you say that everybody's a positive, right? So even then, that approach kind of breaks down a little bit for us. So then we will have to wonder, well, what can we do? And there are a couple of things that we can do. You can play with the parameters of the model if it has any hyperparameters. You could play with regularization, or you could play with the pruning factor for a decision tree. We can at least tune, but not always possible in the extreme case. We could take another target definition. We could maybe try to sample our data set in a different way so that we make it sound that there are more positives than that there actually are, which we will do in a second. If the metric allows us to do so, we could apply misclassification costs, some implementations of decision trees, allowed to do that, where you basically tell them, but be careful when you're calculating your information gain measure, for instance. If you make a false positive mistake, for me that is 10 times as costly as making a false negative mistake, for instance. And then you could spur them along towards making some splits. You could also apply instance weighting, where normally that is being utilized to make it seem that some instances have a higher importance in your data set than others, right? But you could also just say, well, in my case, all of my positive instances have a higher weight than the other instances, which is basically kind of, or applying misclassification costs can then be seen as a special version of instance weighting, where you weight all the positive cases with a similar weight, and you weight all the negative cases with a similar weight, right? But this could also be applied, like if you have some customers in there which are extremely high value, you want to get them right, and they're more important than others, then you can apply instance weighting in that setting as well. And again, an easy way to trick yourself, or to trick a model into believing that some instances are of a higher importance than others, even if it does not directly support instance weighting out of the box, is by simply duplicating those instances in your training data, right? Then they will have a higher weight because they will be scored or incorporated into that loss metric calculation multiple times. Yeah, why bother? Why not just change the loss function directly? Well, exactly because for the implementations that we've seen thus far, they do not make it very easy for us to do so. Although later, or in a second, when we look at ensemble techniques following, they do actually allow us to pick a different loss function. And it's also one of the reasons why deep learning has so many appealing properties, or artificial neural networks in a more general sense, is that they also make it easy to pick a different loss function, because then we will just throw stochastic gradient descent as an optimizer on the weights given a certain loss function. So this will allow us then for more playing room when we really need to drive a model towards steering away from just simplistic accuracy, or also making or taking that imbalance into account a little bit better. Now, with simple models, or if the model does not allow you to change the loss function, or maybe you're not really willing to do so, we will take a look at some other things that we can at least apply to avoid that issue of a decision tree that does not want to make any splits. And at the very least, even although you might not be always capable, because even if you can change the loss function, typically you would like to utilize a relatively convex loss function, and a loss function which is pretty much differentiable, maybe not completely differentiable, but at least pretty much differentiable. At least you can still evaluate based on what matters to you when evaluating your model on your test set. That does not have to be the same loss metric than the loss metric that you utilized to train your model, right? You could even bring in monetary concerns, or value concerns, or cost-benefit trade-offs when making an estimation of how much value your model will bring to the table, and might not be directly the same as the best value for that particular loss function that you've chosen to utilize. So this is the threshold tuning aspect between recall and precision, but you know this already. If you set your threshold very low, everybody's a positive, so you catch them all, but you also make the highest amount of mistakes, or your precision is the lowest, right? Other way around, if you set your threshold higher, you're capturing less positives, but you're also making less mistakes, hence your precision goes up. So these two are in direct contrast. And the point where they cross, typically for well-balanced models, or well-balanced data sets and well-calibrated models, is typically around the 0.5 point in the threshold, but that does not necessarily always have to be the case. Very often that crossing point can look completely different. It would of course be amazing if we can find some model that would give us both, that has a perfect separation of the two classes. In this case, you can find a threshold that gives you 100% recall and 100% precision, but obviously that's not what happens in practice, right? So there will be some trade-off to make between these two. So what can we do? Well, I already spoke a bit about misclassification costs. If you really have to solve this problem where you're not happy with that confusion matrix that you get, and you're not happy with the tuning of the threshold, and you really would like to tell your model, yeah, okay, listen, but for me, false positives are way more important than false negatives. We already discussed a couple of strategies. If we could apply misclassification costs, right, then we have kind of an easy solution for that. So let's say we are working in a case where we have 100 instances, but only in 1% of the cases there is a positive instance. So in the case of 100, I would only have like one positive case, right? It's a bit of a toy example. But then basically, very often if I would optimize for accuracy, and it's very hard to catch this single positive case that is hiding in my data set, most likely what I will end up with is a confusion matrix that looks something like this, right? Where my model has just defaulted into saying, well, you know what, everything is a negative case. That's the best accuracy that I can get. And then in the extreme case of not having any splits in the decision tree, there would be no threshold that you could find that would change this confusion matrix either. Okay. Now let's say that we can apply misclassification cost. So you know this already, we get an accuracy of 99. Looks great, but is not, right? Because I'm really interested to at least catching this positive case, right? And I know that will come at a higher rate of mistakes on the negative side, but that's something that I'm willing to do, right? So be careful when people tell you about accuracy of their models or consultants tell you about accuracy, especially in the case where you're working with an imbalanced setting. So picking a stricter threshold doesn't always work, right, as seen with that decision tree extreme case. So how can I still push my model to catch this positive that's hiding there? Well, if I have a model that allows me to set misclassification costs, then I can solve it that way, right? And the way how these models apply is they say, well, okay, by default we assume that the cost of making a correct prediction is 0, obviously, right? Because there is no cost associated to that. And that the cost of a false negative and false positive is both equal to the same value, is both equal to 1, let's say. So that would be your default accuracy cost matrix that you would get. But I would like to change this, and I might say, well, no, if I could go in there and I would be able to say that making or mispredicting a positive as a negative is 5 times as bad as mispredicting a negative as a positive case, then maybe I would be catching that positive that's hiding in there. So that's what I would like to convey with these misclassification costs. Question will then be, well, what do I set this cost at? Should that be 5 or 10 or 20? What should that value be? And there is something that we can utilize to guide us there. Either you ask an expert, but typically hard to do, or you try to estimate it using real average observed costs, monetary costs, for instance, that's associated to this, but also that is not so easy in many settings. So an easier default case to start from is from the inverse class distribution that you can utilize instead. And as the name suggests, inverse class distribution, right? So if you have 99 negatives versus 1% positive, 1 over 99% times 99%, 1 over 1% times 99%, basically you flip them around, you get a 1 over here, and you get 99 over there. So that would be the configuration if I would work with the inverse class distribution. And then, if I would have a cost matrix, either this one or this one, whatever, I have defined my cost matrix, we can then calculate something, or the way why this works is you can then calculate something like the expected loss. And the expected loss in this case is the loss that we have for classifying an observation X as being of class J. And in the case of binary, this is for multi-class, in the case of binary classification, basically you only have 2 predictions that you can make, either class 0 or class 1. And because the diagonal here of my cost matrix is 0 anyway, and by the way, there is a theorem that states that even although you would not put zeros in the diagonal here, you can convert that to a configuration of the cost matrix where you do have zeros in this diagonal. So you can basically always assume that making a correct prediction has a cost of 0. So even if you would say, but maybe you have different benefits here, and here I would like to put in -1, and here I would like to put in -5, right? You can basically translate that to a configuration where you end up with zeros over here and different values over there. So basically that means that this cancels out, that this cancels out, that you only need to basically say, well, what's the probability according to my model given X that it classifies you as a 1 times the cost of getting it wrong, right? That's my expected loss. And then likewise, what's the probability that you would predict this as being a 0 case times the cost of getting it wrong? And obviously we also know that in the case of binary classification, that this probability is equal to 1 minus this probability, right? So that will also help us to cancel out a couple of things, right? And then the way how you would utilize this classifier, if you have configured it to use this particular cost matrix, is to say, well, now the way how I would utilize this, I will not directly look at the probabilities that come out of there, but I will of course take my cost matrix into account, and based on what my highest expected loss is, right, I will decide whether I should predict you as being a positive or a negative. I will pick the choice that leads to the lowest expected loss or regret, if you will, right? So in this case, if my cost intensity insensitive classifier would have told me, actually it's a 22% risk of classifying or chance that this is a positive, well, maybe I should indeed classify you as positive because I see that if I would assign you to the case of 0, my loss is 1.1. If I assign you to the case of 1, your loss is 0.78. So even although my base classifier predicts me in the cost-insensitive situation a low probability, if I know that this is my cost matrix, I would still regard you as being a positive, right? Because I know that for this particular cost configuration, I'm still better off in terms of considering you as a positive. And it also means that if you then work out the mathematics, right, that you can kind of come up with a new threshold, right? So where is the middle point between when should I classify you as a positive, when should I classify you as a negative? Well, the middle point is at the point when these two losses become equal to each other, obviously, right? So depending on your particularly chosen cost matrix, this becomes your new cost-sensitive threshold, right? And then this basically tells you, well, if it's higher than this value, you're a positive, and if it's lower than this value, you're a negative, given this configuration of your cost matrix. And of course, if you are not using any costs at all, then the cost-sensitive threshold is the same as the cost-insensitive threshold is 0.5 in that situation. So in this case, because 0.22 is higher than the cost-sensitive threshold of 1/6, in this case, I would classify you as a positive. Okay, that's all nice and so on. What this basically means is if I would then use the class inverse cost matrix, that just as well, I can figure out the cost-sensitive threshold in that case, which is then 0.01, obviously, right, which I could utilize then as well. Now this looks okay, but this basically still has the kind of underlying assumption there that if we are not informing our learner of this cost matrix during the learning procedure itself, but this is still something that we apply post hoc on the probabilities that we get from a cost-insensitive classifier, that yes, we could figure out using this inverse class matrix, we could basically find a configured threshold saying, well, everybody above this value you should think of them as a positive. It still would not really help us in very extreme cases like we started from, where I basically, well, no matter how I set my threshold, right, I only can flip between the two choices that everybody's a negative or everybody's a positive. That's a very extreme situation, but it's a situation, as we have seen, that can happen, right? But this leads us to a sort of a theoretical insight, at least, because what this shows me, this class inverse cost matrix, that if I would sample the data set so that the minority class is equal to the majority class, that would be the same as biasing the classifier as if I would use a cost matrix constructed from the inverse class imbalance. And maybe I do not have a way to make my learner aware of such a cost matrix because the algorithm does not support it or the algorithm does not support it. What I can do is I can play with the data that I have available, and I can at least play with the training examples that I have. And from there then, and this is something that you do if your decision tree implementation would not have a way to specify a cost matrix, for instance, and sometimes the specification of this cost matrix can be a little bit sensitive to particular values as well. But this also tells us that we can approach it not from, or that we can approach it from a different angle, and rather than hoping that we can make our learner cost sensitive in a certain way, right? Well, we can also play with our data. That's always the easiest to do, right? And what this tells us is that, well, maybe we start from a situation where I have way more negative cases than positive cases. At least I can pretend that they appear at the same rate. But for that, of course, you're going to apply a trick. And the trick consists of we're either going to apply oversampling, or also called upsampling, or we're going to apply downsampling or undersampling. What oversampling says is, well, if your learner does not support static misclassification costs and incorporating that into its internal loss function that it optimizes for, at least you can play around with the data and just pretend that you have as many positive cases as you have negative cases, for instance. How do you do that? Well, you have two choices. Either you take the positive cases that you have already and you duplicate them. You just copy them over. So that's what oversampling or random oversampling does. You pick a random set of positives and you keep duplicating them until you have as many positives as you have negatives, basically, right? And then you bias your learner in such a way that it believes that both the positives and the negatives arrive at the same rate. Is it perfect? Well, not really, because you're making copies of your data, so it's not like you're adding really new information in there, right? But at least you're biasing your learner. Only on the training data, not on the test data, right? Because on the test data, you still want to evaluate according to the real life situation, right? So you only do this when training your model, so only on the training data. Undersampling then says, well, randomly kick out negative cases until you have, let's say, a 50-50 balance, right? That's maybe more appealing because typically you have so many negatives that maybe it's not such a bad idea to make your data set smaller to begin with, right? But also there you could wonder about maybe there are higher quality negatives that I would like to keep versus lower quality negatives that I maybe want to kick out. Standard undersampling and upsampling does not care about this, it just applies this randomly, and in both cases, or in all cases, these resampling procedures are applied on the trained data only. But given this discussion of maybe you have high quality negatives and maybe you have low quality negatives in the case of undersampling, or in the case of upsampling, maybe you have positives which are perhaps more noisy than others, you can think of more smarter procedures as well. And that's then typically what people call smart sampling approaches, like one of the first techniques that this was called SMOTE, Synthetic Minority Oversampling Technique from 2002. And this one says, well, we are going to apply upsampling or oversampling, so we will take the circles over here because those are the minority class. But instead of just creating copies on top of the same spot, we're going to try to add in a bit more variety in there. And maybe that will at least help our learner a little bit. And the way how SMOTE does so is it says, well, for each instance that you're aiming to duplicate, determine the nearest neighbors and then basically generate a synthetic example somewhere across the path between you and your neighbors. So you do not really create an exact copy, but something that is between you and a friend of you which is of the same class. Right? So you basically try to fill up that area of that minority group here a little bit more densely, rather than just making copies. You can then still also apply undersampling as well, should you want to do so, so you can do both at the same time, obviously, as well. But is this always perfect? Well, maybe not, right? Because you might say, well, maybe if you generate positive cases here, it seems like a safe zone. Over here, that's maybe already a little bit more dangerous because you're closer to the negative class, right? Or maybe if you generate a synthetic example between this one and this one, but it comes super close to this negative case that you have, maybe you can't be so sure of the quality of the synthetic instance that you're generating there, right? Or maybe you can be. Maybe you do want to create a balance between positive and negative in these noisy areas. But so that way of thinking, that's then what caused all of these adaptations from the original idea of SMOTE, like safe level SMOTE, which tries to avoid crossing over dense groups of the majority class, as you can see here. Other types of generating synthetic examples, borderline SMOTE, AdaSyn, MW mode, right? The imp-learn package implements all of these guys, right? Now, two things on this. In the majority of cases, what we find that works best is AdaSyn tends to do a good job, and MW mode tends to do a good job. Remark number two, there is kind of a folklore amongst machine learners that these techniques, they do a good job. They can indeed also increase the performance of your model. But if you would be utilizing a learner which is itself already pretty strong, like a tree-based ensemble technique, some recent works have basically found that sometimes, even although people think that they help, they don't end up helping anyway. So maybe sometimes we are maybe mistakenly utilizing those, also because these tree-based ensembles do allow you to change the loss function. And if you would have a case with a strong imbalance, you could then look at things such as focal loss, for instance, to utilize instead, rather than trying to play with your data like you do here. So this is something that a lot of people started to adopt, but maybe we should not always utilize in every case anymore. If you use a weak learner, like a decision tree or something like that, of course it makes sense, or logistic regression, maybe less so if you utilize something like XGBoost. What else? Yeah, don't expect magic. If you really have a very low amount of positives, it's just generating synthetic ones. It's not going to magically discover some new type of positive behavior, right? It's also not to be confounded with, I think I gave the example already a couple of weeks ago, when I said very often, not only do you have a very low amount of positives in here, but also those negatives are noisy as well, right? The positives are just the cases that we decided to investigate. Does that mean that the negatives are all cleanly negative? No, there might also be still a group of positives in there that we just failed to identify up until now. Do not expect these techniques to start identifying or to start generating synthetic instances over there, right? They don't do so. They only base yourself or themselves on the positives that you do have. If you really believe that there is like some hidden positivity still in your negatives because your labels are noisy, supervised learning is not going to help you, right? And then third, but that's kind of a bit of a weird kind of aspect here. It's not a big deal if you don't do that correctly, but forget that no matter which of these techniques that you end up utilizing, you do need to apply on the train set only, right? Not on your test sets. Now, quite often, as you will see later, if you utilize something like cross-validation, for instance, you already make like internal splits between train and validation sets in your pipeline. And then the question is, well, when do I apply this? Again, do I first apply this on my complete train data and I then go forward with this in a cross-validation? No, ideally, every split comes first. So also ideally, you first split your train data into the different folds that you plan to utilize for cross-validation. You only apply a smart sampling technique within the folds that you're using to train the model, and you do not apply it on the fold that you're using to evaluate your model during the cross-validation. Depending on how good you are with scikit-learn and setting up pipelines, that might be easy or less easy for you in the correct way. Whatever you do, even if you know it's not fully correct, you don't touch the test set with this stuff, right? So that you, in any case, you don't do to keep that set correct. You can try both approaches at the same time, like I said. Yeah, which level do you need to, maybe you can even oversample so that you have more positives than negatives. Does that make sense in some cases? Well, in some cases it does. There have been benchmark studies that have been run using all sorts of smart sampling approaches, using all sorts of base learners, using all sorts of data sets, and basically the answer is that this is something that you need to tune. Starting from a 50-50 balance between the negatives and the positives makes sense. At least you will start identifying some positives or some more positives, but that does not always mean that that's the best configuration to utilize there. And also, likewise, if you use a very strong learner, maybe it's not always worthwhile to do this. So experimentation required with the right amounts of over and under sampling. And what is very likely to happen is that your accuracy, at least, will go down, right? Because yes, you will be identifying some cases as being positive correctly, but that will come at a higher rate of making mistakes on the negative side. But typically, that's something that you're willing to live with, right? If you talk about fraud, well, maybe investigating someone extra is worth it to you if you can catch fraud, because you're dealing with positive and negative. But if you think about that cost matrix, misidentifying a positive is, of course, way more costly to you than misinvestigation or investigating a negative, let's say. So these things were already mentioned, not always worth it when using tree-based ensemble techniques, and neither with deep learning. It's also not very common to utilize that, because there it's better to go directly to your loss function and tweak that one instead. Instance weighting, already mentioned, so then you weigh per instance. Some techniques support that also out of the box. If not, you can apply the same trick as we did for the misclassification matrix or the cost matrix, and you can also decide to duplicate some instances, but again, only in your training data, obviously. Maybe you are trying to do binary classification, but you do not only have the fact that something was fraudulent or not, but you also have the amount of fraud that was committed. Well, then maybe you can try to focus more on the high amount cases by duplicating those only, right? Or in your upsampling procedure, maybe not taking a random sampling of the positives to duplicate, but maybe weighting that based on their underlying amount of fraud that was committed. Otherwise, if you don't do that, typically you will end up with a model that's maybe not so bad at identifying positive cases, but is of course focusing on the low fraudulent positive cases, because typically these are also easier to detect, right? But those are not the ones that you're particularly interested in. You're of course more interested in getting the high value cases more correct. So then you're basically applying a form of instance weighting by either telling the technique directly or by just playing with the data level or at the data level and duplicating those instances. Now, of course, what will happen is this is, of course, a perfect way, even if you have a well-calibrated classifier, like a logistic regression. If you play with the distribution of positive negatives in your training data, what is going to happen for sure is that now you end up with a non-well-calibrated classifier, because you have made it believe that positive and negatives is something that happens at the same rate, right, which is not the case in real life. So the probabilities that this thing now gives you will be not well calibrated anymore, right? There will be not a probabilistic interpretation that you can take on those anymore, right? So we saw that for an equally balanced data set and a well calibrated classifier, it will put the cutoff neatly at 50%. But if tomorrow you give it like an instance and it tells you, this is 70% fraudulent and we take 100 of them, not 70% of them will commit fraud, right? So we have lost our probabilistic interpretation at least. So it's not a calibrated view anymore on the probabilities. Now, in the case of binary classification, you can apply like a simple correction on the probability distribution that a model gives you to correct on that. And basically, the upper image here is the probability distribution that you would get from something like logistic regression, but after you have played around by using oversampling or downsampling. So you see that now it's giving you probabilities like 80%. But it's not because you take 100 of those that 80 of them are actually going to commit fraud, right? So by applying that formula, basically what you do is you squeeze all the probabilities back to their a priori kind of distribution or rate, right? If the only thing that you want to do is rank, right, then this doesn't matter. If it's really important in your case to have like a good calibrated interpretation of these probabilities, then that's something that you can do. Okay. Now, in any case, whatever we utilized, so we know now that accuracy is very often not really the metric we should look at. Recall and precision are more important, depend on the threshold. So are there other techniques or other metrics that we can come up with, and perhaps metrics that do not depend on that particular choice of threshold? Because that's still a little bit bothersome that even now we can start to identify some positives in our confusion matrix. We still need to decide upon a particular threshold. And especially if we want to compare different models with one another, maybe it would be nice that we can have something that looks, well, that can look across all the possible thresholds that we could configure. And indeed, there is something that will help us out with that, and that something is called the ROC curve. So that's basically a way, so this will give us an opportunity to define a metric which is not dependent on a particular choice of threshold anymore. So that's quite advantageous. That will make it easier for us to compare maybe a couple of different configurations or different models that I have trained, and easier establish, okay, which one of you is now the best model for my particular use case. So we'll look at the ROC curve, but first we will go for a 15-minute break. So our next classification tool, or performance evaluation tool for classification rather, will be the ROC curve. Also probably already well known to most of you. So let's take a look. We will make a curve like you see here, the blue one. And the two axes are sensitivity, which you already saw. That's nothing else than recall, or very closely related to recall, or the true positive rate, but rescaled so that the min and the max is between 0 and 1 in all cases, and same for the x-axis, also rescaled so that it's between 0 and 1. But there we place 1 minus the specificity, which is equivalent to the false positive rate. So how many cases, or what's the percentage of the cases you're getting right, basically on the y-axis. So this is good news. The higher this gets, the better. False positive rate, this is kind of your false alarm rate. What's the rate of false positives that you're making? So the more that you go to the right, the worse news it is, basically. And it doesn't mean that, well, but basically this says is the way how we construct a plot like this will basically loop over all possible cutoffs that we can take, so all possible thresholds that we can configure. We will calculate the true positive rate and the false positive rate at that specific threshold, and then we pin a dot in the map, basically. So for every possible threshold, we put a dot down. So it's a combination of true positive rate, false positive rate, and basically by following these thresholds, you kind of can construct a curve like this, or you draw a curve throughout these different points that you have placed on this map. Note here that this curve is non-convex, right? But you can make it into a convex curve by basically, well, taking the convex outer shell. And that is related to a theory that says, well, if you have 2 points on a curve that is non-convex, so it looks something over here. So you would have a curve like the one, but maybe a bit more extreme, like maybe something that does something like this. That basically you can take the convex hull of that curve, and in many cases that's the one that you see plotted instead. The reason being because in theory at least what it says is if that you can find a configuration for a model over here and over here, that also all possible combinations across the outer curve or the convex curve can be found as well. But it doesn't really matter in most cases. You can find both as well in real life. Here we just draw the normal one instead. Okay, something else that we will do is, so obviously what would be the best possible position that we can find ourselves in if we would have a model for which there exists a threshold that can bring us all the way up until the top left, right? So a true positive rate of 100% and a false positive rate of 0%, then basically we are perfect, right? So then reaching the top left corner is the best that we can hope for. But in most cases, that's not what you see, right? And what you see if you go across these thresholds is exactly the trade-off that, well, indeed, you can find thresholds that allow you to capture more of your true positives, so to increase your recall rate in this case when you go up, but that will come at the cost of making more false positives as well. So you will be pulled to the right as you go up here. What you can then do, so that means that if what we can do next is we could calculate the area under this curve or the AUC value. And if that value would be 100, that basically means that you have a curve that reaches this top left corner. That would be a perfect model, right? In many cases, the AUC, the area under the curve value will be less than that. And that has a nice interpretation, this AUC value, because it is the probability that you would give or that your model at least, gives a randomly chosen positive case a higher score than a randomly chosen negative case. So hence 100% as the best value, because that one means, well, no matter which random positive case that you give me and no matter which random negative case that you give me, the positive case will always get a higher score than the negative case. If that happens in 100% of the cases, you basically have perfect separation. What's the worst case that you can end up with? Well, an AUC of 50%, meaning that if you give me a random positive case and a random negative case, what's the chance that your model will rank the positive one as being higher than the negative one? If that's 50%, you basically have a coin flip model, right? A model that's handing out random probabilities, if you will. So the worst model configuration or the worst curve that you can end up with is basically this diagonal line that you see here, because your rate at making, or the rate at which you make false positives, increases at the same rate as by which you identify more true positives, right? So that's basically a model that gives everybody a random probability. If you have a model, or if your ROC curve would be under this line, right? So you would get an AUC value which is less than 0.5. You would be better off at just flipping the predictions that your model makes around, and you have it flip over the diagonal, right? It can happen in some cases that your model first increases, but then goes to the right and maybe goes under the line, right? It's a bit rare to see, but that's something that can happen. So it's not that the full curve needs to be above this diagonal. It depends a little bit again on what your data set looks like, which particular model configuration that you utilized or how you tuned your model. But generally, you do expect to see a major part of the curve to lie above this diagonal rather than under it. Now, because this curve loops now or goes over all the possible cutoffs that we can take, this also means that if we then take the area under this curve, that this is a threshold independent metric. Or better said, it basically makes a summary over all the possible thresholds, right? So it incorporates every possible threshold that we can pick. So it goes over all the behaviors of our model that we can see in this confusion matrix in terms of true positives and false positives that you see, or the rate of those rather. What else? Yeah, we go over the thresholds from 0 to 1, right? So we can kind of wonder where is the 0, where is the 1? Well, remember, if I would take a threshold of 0, that basically means that I identify everybody as being a positive, meaning that in that situation I will have a perfect true positive rate, but the worst false positive rate. So the lowest threshold is here, the highest threshold is over here. So I go from 1 to 0 by following this curve from bottom to the right-hand side. Right. So here is how you make it, right? You could just go over a range of thresholds, but again, here it only makes sense to calculate the lines for the distinct values of the probabilities that my model predicted for this test set ranked from low to high. For each of those thresholds, I can calculate my confusion matrix with true positives, true negatives, and false negatives. I can then calculate the recall value, right? As we saw before, I can calculate the precision value. They kind of correspond similarly to the behavior that we saw previously, right? That in the case of my recall going down as my threshold increases, my precision will go up because I become stricter, but I also detect less positives from my data set. So that's the same threshold that we saw previously. How you go from recall through the true positive rate, it's exactly the same. So we don't need to do anything there. My recall is a true positive rate value. False positive rate, on the other hand, well, we don't really look at precision, although it's somewhat correlated with precision, as you can see, right? But false positive rate, we look at the, well, what's the highest amount of false positives that you ever make? Well, it's 5, right? In this threshold, you're making 5 false positives, so you're making the worst false positive rate that you can make there, right? And of course, the best value will be 0 because there will be a threshold at which you are not identifying anybody as a positive anymore, right? So your false positive rate will have gone to 0. So here your lowest value will always be 0. And hence for recall, obviously your highest value will always be 1, right? And hence why you might hope that there is a configuration where you can reach this spot, right? Okay, what does this now allow me to do? Compare different models with one another. Which I can do on the basis of the curves themselves, which is not a bad idea, in all honesty. But of course, here the problem is that sometimes these curves might cross with one another, because depending how the underlying behavior of my models are across their thresholds, my curves will not always be one completely surrounding the other one, right? In the case of having to pick here between the green model, for instance, and the yellow model, the choice is clear because, well, for every possible threshold that I can find, it's kind of outperforming the yellow one. So the yellow one is out here. But if I would have to make a choice between the red model and the blue model, it's less clear because, yeah, first the red model does better, but then in terms of recall, the blue model does seem to reach a higher point at a lower cost of making false positives. So then you might want to inspect these curves a bit more closely. Now, this being said, you can then calculate the area under those curves and you can make your decision based on, okay, which one of these 4 models has the best AUC value, right? And I'm going to pick that one. But here too, it depends a little bit on how you plan to utilize this model in practice, right? Because it's not always necessarily the case that you're interested in the full span or the full area of this ROC curve, right? And think a little bit about your context. So what I know is that, of course, how steep this model or this curve is in the beginning is kind of related to, well, precision, because given a certain false positive rate that I'm willing to live with, right, which model brings me to the best recall value? If you know in your configuration that, well, listen, I'm only willing to live with a 10% false positive rate, but not higher than that, well, then basically everything that follows after this 10% along the x-axis is not of interest of you. You're only interested in which model gives me the best recall value given this 10% level, and then the red one would be the best one. If you would say, no, for me it's important that I identify, I'm looking at rare diseases, for instance, and I do need to capture 90% of the positives that are in there, right, because I will be checking them. So then you know that you need to reach this level, and you would be interested in, okay, which model gets me there at the lowest false positive rate, and then you will pick the blue model. So it's not the case that AUC will always summarize these curves in such a way that they will result in the model being chosen, being the best one for your particular context. So think back a little bit of, okay, what do I expect, and try to make a bit of a closer inspection of the performance of your model. But we tend to always try to put it into one metric, but these kind of trade-offs, of course, you do see them here between the red and the blue curve as well. Something else that people utilize a lot as kind of an alternative to the ROC curve, which contrasts true positive rate sensitivity versus false positive rate, 1 minus specificity, is doing it with recall and precision curves instead, as you see here on the left-hand side. You might think, well, these are more or less the same, right? Because recall, okay, we have that over here on the x-axis, but we had that over here on the y-axis, so that's exactly the same. So what about precision, right? Precision is not, we know that from this overview, precision is not exactly the same as false positive rate, but we did see that there was like a correlation between them, right? If false positive rate is high, of course, my precision tends to be low. If false positive rate is low, my precision tends to be high. But of course, precision does not go necessarily between 0 and 1 like the rate of false positive does over there. So they're kind of the same, but not exactly the same. And it shows here, you can kind of generally see that if I look at these two curves, like especially like this, what is it, orange one, for instance, over here, or this purple one, they tend to show like not very good ROC curves. In terms of precision, yeah, also the blue one sticks out as being pretty low. Also the purple one sticks out as being relatively low. But this black one over here is a little bit strange, right? Because this tends to, at least according to this curve, tends to do not such a good job. And if I look over here, it's kind of in the middle if in terms of ROC curve. So what's going on there? And of course, what is going on is that for precision, right, we spread out the behavior from a precision value of 1 to something like 0.1 over here, right? It's rare that for precision we will reach 0 exactly. Of course, the reason why all these curves jump up from the beginning is because of that numerical issue that you have on the left-hand side. But ignoring kind of these points here, and if you would start from this bunch, but here, of course, your false positive rate does go all the way to 0, right? And what is happening here is that, especially in the case of you working with a very imbalanced data set, that actually a majority of what is being kind of shown over here in this curve actually gets squished on top of each other over here in your ROC curve, right? Because your false positive rate tends to, if you express it between 0 and 1, it tends to lead you or give high increases for recall with only very small changes in the false positive rate over here, whereas versus precision, the increases in recall that you see, you do see the drop in precision more clearly associated over there. So that also means that, well, if you're only interested in keeping your precision as high as possible, so in other words, keeping your false positive rate relatively low, let's say you're only interested between 0 and 10%, then of course you would zoom in on this part of the curve, of the ROC curve only, and then you would start to see that for this area or this zone of the ROC curves, then indeed that black model would be, and you can kind of see it that it's at the bottom here as well, right, that it's not really doing a good job, but they just appear to be very similar by looking at the ROC curves over there. So summarized, both of them use sensitivity, both of them hence use recall, same thing, or the true positive rate, also the same thing. So for that, they are indeed equivalent. The precision recall curve uses precision, which is the rate of predicted positives that were indeed positive, right? So there it depends on how many of the predicted positives are indeed positive. And the ROC curve uses 1 minus the rate of the negatives in the data set that were predicted as such. So a key difference is that the precision metric, and hence why it doesn't go all the way to 0, the precision metric does not account for the true negatives. So if you only look at recall and precision, you're kind of ignoring the amount of true negatives that your model is providing you given a certain threshold. And the reason why, and especially in balanced cases, there is some logic behind that, because very often you have a lot of negatives, and very often it's not so hard to classifying them correctly, even if you just say that everybody's a negative. That true negative mass that you have in your confusion matrix will typically be the largest mass out of these 4 quadrants that you have in your confusion matrix. So if you do put that into a curve, well, especially for an area where the true negatives make up a significant amount of your confusion matrix, your lines will get squished on top of one another. So sometimes ignoring that and using precision instead, rather than the false positive rate, makes more sense to get a clear view. So precision measures the probability of a sample classified as a positive to actually be a positive. The false positive rate measures the ratio of false positives within the negative samples. Now, generally speaking, because the ROC curve incorporates all 4 quadrants of your confusion matrix, you would say that that's the preferred one. And hence why in a lot of settings, people will utilize the ROC curve to kind of show performance of a model rather than the precision recall curve. On the other hand, as just stated, if you're dealing with an imbalanced data set, then your false positive rate tends to increase more slowly because the true negatives take up a significant part of your confusion matrix, making the false positive rate smaller, but precision being unaffected by this. And that's exactly false positive smaller. It seems like these curves in the beginning, they have the same kind of of behavior, right? Whereas actually precision shows us that this is not really the case, right? So either two choices. If you would utilize the AUC values, they would be more influenced by this part of the curve rather than here where everybody is stacked on top of each other. So when you're working with imbalanced data, do two things instead rather than using the area under the ROC curve. If you work with an imbalanced data set, use the area under the precision recall curve instead to have one metric that tells you what is now your best model. Or you only calculate the area under the ROC curve, but only up until a certain false positive rate value and not beyond that. Most people will stick to calculating the area under the precision recall curve. So especially for imbalanced data, that's a good idea. This is the other example where you only look at the false positive rate. So if you look at this ROC curve and you calculate the two AUC values, then obviously the blue one has the better value. But if you are working in a very imbalanced domain, well, it might only make sense to look at the ROC curves up until the 0.001 point. And in that case, your AUC value would tell you that, and here now it's clear, that the orange one is actually outperforming the blue one in that case. So be a bit careful if you work again with imbalanced data that maybe the area under the PR curve might be a better choice to utilize than the area under the ROC curve. So similar concept for the precision recall curves, but do visually inspect your curves a bit and try to understand them a bit as well. There are some other approaches that exist like weighted approaches, but they are less commonly utilized. And these figures are taken from this tutorial page as well. There are other metrics that people utilize sometimes as well. So these are by no means the only ones. Coming up with like a classification metrics is a pastime or a hobby for a lot of people. So here you can see another approach which is based on ranking the scores first. So you first sort your population from those having a high score to those having a low score, and then you retain like a certain percentage of them as ranked by their score. So what if I look at the top 10% of cases? What if I look at the top 20% of cases, the top 30% of cases? If I retain no one, yeah, of course I can't meaningfully draw anything, so I can basically ignore that part of the curve. But from the moment that I have some people, like 10%, well, how many positives do I expect to get in the top 10%, right? Well, hopefully all of them, right? But typically the real situation will not be that everybody in there is like a positive. So you basically look at the rate of positives as you retain more cases, right? So that's another approach. And then you can also define like an area under that curve. It's also sometimes called a Lorentz curve or a power curve or a captured event plot. So there are different names for that. And again, here the diagonal is kind of what you would get if your model would just be handing out random probabilities, right? So typically your model will follow the line in the middle there, and then you can calculate the area under that line, and you subtract the area under the random model, and the thing that you're left with then, which is the AR value in that case, is then it's actually equivalent to 2 times the AUC minus 1. So there is kind of a quite direct link between the AUC of an ROC curve and the AR value that you see in this figure over here. Something related to this is the concept of lift. Let's say again we have a random model that's handing out random probabilities, so we're just calculating the a priori occurrence of someone being a positive. We take the top n% of cases, we see how many of them are a positive, right? So let's say 10 out of 100. Now we do the same for your model. Your model says 60 out of 100 for the same top 100 cases, meaning that your model is 6 times as good as if you would do it randomly, right? It's kind of the same thing as here, except that here you're comparing with, for instance, a random model. So that means that if you have a lift of 1, that you're equivalent to just randomly picking cases as being positive, right? So that's the red line that just states 1. That's your random model, right? And then the blue line is the lift that your model gets over the random or over the a priori situation. Of course, this will depend on the number or the percentage of the population that you retain, right? Because, of course, the more, if you check everybody, right? If you decide to check the full 100% of the population in your test set, yeah, then the number of them that are positive is the same amount as if what a random model would have given you, because in any case, you're keeping everybody or checking everybody. So they meet each other at the 100% line over here, right? But typically you hope that your model stays higher than this random model or the a priori situation for as long as possible. This is cumulatively done then, so that's why they meet. but you can also do that over distinct deciles as well. You first take a look at the top 10%, right? And you see how much better you are than a random model. And then you look at 10 to 20%, 20 to 30%, and so on. And that's the bar chart that you see over there. That's also quite common. And then here, this model that you start with, this random model, this is also commonly done not to compare, like, for instance, how good are you to the a priori situation, and that depends, of course, at the rate of positives, at the classification, or at the class balance that you have. But maybe you have a model in place already, right? And then the question is, well, how much better are you than that model that we have in place already, right? And then that's what you're contrasting against. So then you calculate the lift not to the random situation, but to a model that's already in place. And what this kind of reveals is kind of the context, or again, the use case, or the notion that in many situations, you don't really care that much about the specific probability distribution. This is mainly that this is more like a ranking-oriented metric, because you care at, is my model not just capable to separate these two groups from one another, these negatives and these positives, but knowing that, for instance, I'm only capable to take a look at the top 20% every month anyway, whatever you do in the rest of that 80%, I don't basically care that much, right? Even if you get it completely wrong over there, so what? I will not look at that anyway. So what I'm mainly interested in is within this top 20%, how much better are you than a random model or a model that we already utilize, right? Because that's the only amount. I will only look at your top 20 scores. So basically, that's the zone that you should do well in. The rest of your scores, whatever, right? Maybe you're able to separate the classes pretty well, but I'm only interested in that performance in the top 20%. And that concept of making a short list of cases, or taking a ranking-oriented perspective on evaluating models, happens quite often. Also for recall and precision at n, same concept. For the top n cases, the top n scored predictions, what's the recall there? What's the prediction? What's the precision there? So I'm not calculating recall and precision for all of the instances that I have, but only on those that got the highest score from you. So for shortlists, and that happens very often, in every kind of business setting, we don't have budget to check everybody. We don't have marketing budget to send everybody a promotion that gets a high probability. We'll only do that for the top 100 cases every month. So how well are you doing within the top 100 cases? And again, that makes training of models even a little bit more complicated, because before we were kind of dealing with the issue that, damn, they focus on accuracy, but if you have class imbalance, that's really not what we want. So we need to kind of fake our way out of that to make it appear that we have as many positives and negatives. And now what we're adding on top of that is basically saying, and by the way, we only care about your top 100 predictions. What you do elsewise is actually maybe less important to us. Of course, these two concerns are related, because the better you are at separating the two classes, probably also the better your top scores will be, but they're not completely the same thing. And again, also here, if you do have the opportunity to change the loss function of your classifier, there are more ranking-oriented loss functions available as well, right? Learning how to separate two classes is not necessarily the same as learning how to rank the positive cases as well. And they are related, but there might be slight differences amongst both concerns. Where do you also see this being very common, this idea of recall at k or precision at k, is when working with recommender systems. Because also there, you could give me a probability for all the movies in the world, telling me what's the likelihood that I will like that movie. You're not gonna offer me or tell me about all the movies that got a score higher than 50%. No, you will just say, I will take the top 3, and I will show those on the homepage, right? And then you're basically only interested in what's the recall for that top 3, right? If you like all 3 of them, fantastic. If you like 0 of them, even if you like number 4 and 5 and 6 and 7 and 8 and 9 and 10, right? We missed a chance with those top 3, right? So I really want to do well in that top 3 kind of prediction, or the scores that I'm given, and the rest of that distribution, or that kind of prediction output, I'm less interested in, right? So also very common to see this concern in the setting of recommender systems. Other alternatives, there is stuff like the H index from David Hand, which was proposed as an alternative to the AUC. It's a nice alternative, actually has some nice theoretical advantages, but it's less commonly utilized in practice. You have things like the KS distance, the Kolmogorov-Smirnov distance, which is a separation measure against another ranking measure. Basically, is the distance between two cumulative score distributions. So again, we have it's basically equivalent to drawing an ROC curve for model 1, or scorecard A as it's called here because it's an example from credit risk modeling. It's an example for model number 2, right? And then basically we look at where the distance between a model is the highest between a diagonal model, and then that's basically the KS distance. And the idea here is too that the larger that this black line is, clearly it's larger for the blue model than it is for the red model, the better the model is, right? So the further away your maximum distance from the diagonal model, the better you're doing. And then there is other things, like we could take a look at the score distribution in terms of my positive cases and my negative cases. And also there, if I would plot both distributions, this is nice, right? Because my group of negatives and positives is nicely separated. This is less nice because my probabilities overlap in a lot of cases. It's not probabilities here on the x-axis, it's score, but it's because they already made the conversion from a probability to a score, but it's the same thing there. And also there, then we can basically try to get a distance between these two distributions, and the further away that they are from one another, the better, basically. It's almost like taking the Euclidean distance between the two means, but by taking the standard deviation of them into account. And there is the divergence measure as well, which splits up this standard deviation as well for the positive cases and the negative cases, rather than using the joint or pooled standard deviation. But same question, how far away or how separated are two distributions from one another. And also there clearly, well, the higher this is, the better probably the separability of the two classes that I have here. And just to show you like how you can go even further, so this is kind of an illustration of think a little bit for your setting what matters. Don't always stick too closely to one of these pre-made evaluation measures. Think about what matters in your use case, right? This is a more automation-oriented approach. So we have here both the score distribution for the negative cases and for the positive case, so it doesn't look all too bad, right? And we need to decide upon a threshold, right? Let's say that I'm not taking the top K cases, but I'm kind of deciding upon a threshold. And I would say, okay, maybe a good configuration for my threshold would be a rather high one if my focus is on precision. That's what we have just discussed. Right? Maybe I'm deciding which cases should get an additional manual check or something like that, or I'm deciding upon something. And if I focus on precision, that means I do not want to capture maybe all of my positives, so recall is less important. But for the ones that I do predict as positive, I do not want there to be a lot of mistakes. Right? Well, fine, then you pick a threshold over there. Accuracy would then be more over here, a good middle ground, a balance between recall and precision. But again, here, we assume that we have balanced classes and that they are of equal importance. And then this would be recall. We want to capture as much as positives as possible, even if it comes at the cost of making more false positives. But what you could also think about is obviously, well, why don't we utilize two thresholds instead? Right? In a real-life case, let's say that this is a model that predicts whether or what the likelihood is that someone will not pay back their loan when filing an application. Basically, would say, well, if the predicted probability is below 0.2, right, we will immediately accept you, right, because you're safe enough. And when your probability of defaulting is above 0.8, we will immediately reject you because you're too risky for us. And maybe what we'll do when your probability falls in between those lines, then we'll do an additional manual check. That's also a way very often how models get deployed and get utilized. So then you're basically playing with two thresholds rather than one. And maybe that's in that case a more sensible approach. And then basically the question is not, okay, what should then these specific two thresholds be, but also how close to each other can I bring them? Because the larger that this gap is between these two thresholds, the more people that I need to pay to do manual checks, right? Which is also typically a concern. I could decide to collapse them into one threshold again, and then basically I've automated everything because everything is getting automatically rejected or automatically accepted, and I don't have to pay anybody, right? And if I set my thresholds at the outer boundaries at 0 and 1, then I'm checking everything manually. So what I could do is I call 1 minus the distance between these two thresholds my degree of automation. That's one concern. And obviously the other concern is what's my accuracy level, right? And then I can find the best trade-off between how many cases do I want to get correct, assuming that my humans do not make mistakes, right? How many cases am I getting correct? So all the mispredictions here come from my thresholds being too much to the middle here, versus what's the degree of automation that I can get out of there. So then you're kind of contrasting these two concerns, both like model performance versus how many people am I paying to do these manual checks. And very often in real life, when people look at results of models and they talk about, well, the difficulty in terms of expectation management, and the model is not performing as well as we had hoped, and it is still making some mistakes. A model will always make some mistakes. It's important to see a model more in the broader context, where it gets embedded into existing business processes like these, and taking a step back and maybe also taking these costs into account. Now, that was classification. Similarly for regression, of course, there what you could do is, again, typically hypothesis tests on your coefficients and getting confidence intervals out of them. That's all nice and dandy, but we have already seen last time that we maybe care a bit less about those significance tests. So R2 is a value that also oftentimes gets mentioned. By all means, don't calculate it on your trained data. Also here too, the coefficients of determination is something that you would calculate on a test set of data. And typically it gets explained as the proportion of variation in your target that is captured by the regression model. And it basically is 1 minus, so to basically flip that around, SSE, and then SSE is kind of the SSE coming from your model, right? Because there is a little head, divided by this thing, and this is kind of your baseline value, right? Where you would use a dumb model, an intercept model only, if you will, right? Where you only predict the average for all of the cases that you see. And then basically what this assumes is, well, obviously this will hopefully, right, be lower than this, and then you subtract that from 1 to basically flip that around. But okay, there is a bit of a weird angle in here, and especially if you would be dealing with outliers or noisy cases or strange behaviors in your test set. The problem with the R-squared value is basically that the definition of its ranges are a little bit strange, right? So obviously the best value that you can get here is 1, right? Because if I make the top part here 0, that means that my model makes 0 mistakes, right? 1 minus 0 is I have a perfect model, R-squared equal to 1. Now, what's the worst value that I can get here? Exactly, negative infinity. Yeah, not 0, but negative infinity. This assumes that the worst possible model that you can make is a model that always predicts the average value. But let me tell you, of course, you can come up with models that are even worse, right? Models that just predict all over the place and are completely wrong in the case of regression. They will even do worse than that average value. Now, of course, if you would end up with something below 0 here, right, you would kind of wonder, at least then you know that if you would switch back to a model that just predicts the average value all the time, that would already be a better model. But again, yeah, the average value of what? Train versus test set, right? It's the average value of the train data, obviously. Who knows, maybe in your test data that would already work less well given a particular target that you have in front of you, right? If you're dealing with something that has a high degree of volatility, that might also already work less well. And then secondly, it depends a little bit on the behavior or the characteristics of your data set that you're running this on. So the influence here that you can have on your R-squared value is quite heavily driven by, let's say, sporadic but extreme mispredictions. If you have a test set with 100 cases, and for most of the cases your model does a relatively good job, but there are only a couple of cases in there for which your model gets it wrong, but in those cases it gets it completely wrong, right? You can already push your R-squared value pretty close to 0, or even again below it, right? So again, it's kind of a trade-off between that L2 norm and L1 norm concern. You see a square in there, so this is more of an L2 concern. So it's not simply about, well, what are the number of cases in which you're getting it wrong, but much like what is the amount that you're getting it wrong by, even if it's just on a couple of cases, and then especially if you get it wrong by a large amount, that will drive that R-squared value down. That means that in terms of interpretation, if we look back at classification and that AUC value had a nice probabilistic interpretation. And we knew, okay, 0.5, that's the worst, 1 is the best. You can kind of expect that if you go 70% and beyond 80, 90 even, that you have a very strong model. Here, well, what's a good R-squared value depends kind of also a little bit on, yeah, how well is that average model already doing to start with, right? If that turns out that for this particular data set, that an average model is a very bad model, right? Of course, then how well your R-squared value is will be closer to 1, right? Because your model, hopefully, will then do much better than that average model is doing. But if it turns out that on your particular data set, an average model is already not that bad, well, then your R-squared value will not be that impressive, right? So you're always comparing with that baseline model, which in itself is not a bad idea, but it can lead to kind of interpretations of, oh, my R-squared value is only 30%. What a pity. Well, it's a pity in the sense of that you know, okay, you're not doing that much better than an average model, but maybe that average model is already in absolute terms not doing a bad job, right? So it's important to keep that in mind and to contrast that as well. So better is to either calculate an RMSE or mean squared error value directly, or mean absolute error as well, to kind of then know, okay, what is that quality of that average model? Not I'm contrasting myself versus that average model, but just in absolute terms, how many mistakes or what's the size of the mistakes that I'm making? Similarly, and this gets way underutilized, but can be extremely informative, and it's very simple, but look at a scatter plot of your predictions. Contrast your predicted values with the true values. And of course, of particular interest is then, why is this case over here, right? I mean, the true value is high. I grossly underpredicted the value. Let me take a look at that instance. Why is that? Which features am I missing here that could have helped me to predict this instance better? Maybe it's a noisy one and I should have removed it from the data set to begin with. So looking at these cases where you get it the most incorrect, it's not a bad idea to do based on an analysis like this. Like the idea of a scatter plot is that you then zoom in on particular regions or instances on which you're not doing a very good job. AIC, BIC, these are more things to compare models with one another, taking into account the complexity of the model here expressed as the number of parameters that you utilize. But yeah, in any case, in the models that we utilize so many parameters that maybe it's of bit less importance to us. R-squared adjusted is something similar where it also tries to account for the complexity of the model, which actually most implementations utilize, even if they just call it R-squared. There are many others here as well, but like I said, for our case, typically what we end up doing is picking something like MSE or the mean absolute deviation or RMSE and looking at something like that instead. Or again, trying to put like a more monetary concern on our regression values and looking at those. BSZ tuning, that's a bit of an older approach that you can look up where you say, okay, maybe I can only use ordinary least squares, something like this, but I do know that my loss function actually is something more like this, or it is something more like that. So how can I then bring my existing model more in line with the actual loss function that I had in mind? Again, nowadays, just use stochastic gradient descent to train a simple artificial neural network on top of this, but things like that exist as well. This is not so bad either as an idea because it's kind of related to something that the ROC curve tries to do, but in a regression context. Because also here, and going back to that idea of R-squared, kind of the trade-off that we want to see is, am I either getting it a little bit wrong on the majority of instances and maybe getting it very wrong for very few of them, or am I getting it quite wrong, but for all of them? Like what's the L1, L2 trade-off over here? And this is better shown in the regression error characteristic curve. Here what I'm doing is I'm increasing a tolerance around my point prediction, and that can be expressed in typically in relative terms, right? So instead of saying, well, what if we would not say that your model predicts 1,000 euros, but something between 1,000 euros, 5% above and 5% beneath it, right? So now we are converting our point predictions into intervals, basically, and it links back to that score that I started explaining at the beginning of today's session as well. And then I look at, okay, if we work with intervals of regression, that's basically binary classification again, because then either the true value is in that interval, or is not in that interval, right? So as I'm increasing the tolerance or I'm increasing the size of that interval, I can of course expect that more and more points will fall within that interval. With 0, that will be very few, because that needs to mean that your true value needs to match exactly with your predicted value. But from the moment I start with like a percentage point, you can see that that accuracy shoots up, will increase and increase, right? And this is then interpretable like you would interpret an ROC curve. Maybe reveals a bit more in terms of, okay, maybe if this shoots up very rapidly, that means that actually the majority of my predictions are very close to the predicted value, right? Or the true values are very close to the predicted value. And in this case, well, this shows me, well, I can get quite rapidly to an 80% level. So for 80% of my cases, my predictions are actually relatively close, or in a 1% distance from them, right? Or 10% distance from them, rather. But then there is a remaining 20% of my instances for which, yeah, they're probably further away from what I'm predicting, right? And that already reveals that trade-off or these two concerns a little bit better. Some basic validation checks. Do check residuals. That's also a good idea. Check variables that get extreme coefficients, especially if you'd have applied regularization or large weights. Check signs of coefficients. But that goes for any model. Always be careful by just training and then looking at the AUC. It's also for classification a good idea to take a look at your top mispredicted instances. Like you have a positive, and your model gave a probability of 0.01. Take a look at those, right? Would you also be confused? Is that because that was mislabeled? Is that because something went horribly wrong? So doing some hand-picked instance investigation is often a good idea as well. How about the top correctly classified ones? Are these indeed the easy cases? So do some spot checks, do some basic verifications to make sure that your model, that when it is making mistakes, at least you can kind of understand that, okay, I can see that this is a hard case, or I would also have had a hard time to do that as well. And like I already mentioned, be careful when trying to extrapolate from training data. There is a difference between predicting the future with lagged variables and your target being in the future than extrapolating from training data. So yeah, using the year as a feature, we already saw that in the pre-processing session as well. So this comes back here. But also that applies to all model types, right? Also for a decision tree or a KNN model, if you go beyond the bounds of your training data, you kind of know that you're in a dangerous zone there as well. We spoke a lot about the evaluation metrics and trained test set. Very briefly, I already mentioned something about cross-validation. So we do need to look also like, what's this cross-validation stuff then all about? Oftentimes gets mentioned in the same breath as evaluation as well, although the concerns at first or at the outset are a little bit different. Your test set is really mainly meant to evaluate your model and get a clear assessment of generalization capability of your model. Cross-validation, on the other hand, is a way which is primarily meant to help you tune the hyperparameters of your model, not necessarily itself as an evaluation approach. So there is two concerns. One is evaluation, as we have seen so far. Cross-validation is more meant to tune the hyperparameters of your model. It's also utilized to help you with model selection as well. So what's the idea there? Why do we utilize it? So this is basically what we've been seeing so far. We have a train and test set. We construct a model. We can get an evaluation on our train data, but we know that's basically trivial. So typically what we then do is we say, okay, that final model or final evaluation is going to be made using the test set. Okay, clear. We did that already. And then we can either be very happy with the results or we can be unhappy. And then we have to go hunt for a new test set and do it all over again. We already saw that with our decision trees, we can also split our train data in a train and a validation piece, and then we utilize that validation set to kind of inform us based on some metric, like when it is time to stop training, and then utilize that as a final model. But still in that case, you do need to evaluate it on your test set, because you still want to know, okay, if I then take this decision tree, maybe it did not overfit on this particular piece of training data that I gave it to, but still over time things might have happened that still caused this decision tree to not do a good job, even although it is not overfitted, right? There can still be volatilities in the underlying data that cause me that I have to test it out on an unseen piece of out-of-time test data. Now, this reveals kind of, or this story like, okay, what I would like to do is I'm kind of stuck here, because on the one hand, at least starting with this situation, I might be disappointed with the results here, and then I would like to go back and try something else. But then the problem is if I do that all over again, well, at some point, my test set is becoming more and more polluted in that sense. I'm then overusing it. So what I then could do is, okay, on the one hand, I would like to keep my test set until the very end. But meanwhile, in this development cycle, I still would like to figure out, okay, but which model can I construct for which I can already prove that probably it is not so bad at generalizing before kind of spoiling my test set. So how do I help to tune and select my best model before I bring it to the finals, right? And have it work on that test set, or bring a collection of models to that final test set, if you will. So I would like to have something like this, where at the very basic setup, I could split into a train set, a validation set, and a test set. And then at least this approach, I can say I use my train data to construct my model, I evaluate it, but maybe I'm unhappy with this, so I can go back and try something else, and I evaluate it again. And the reason why I did a split is because I already want to get some assessment of generalization capability during my development, but I do not want to spoil my test set, and allowing myself to go back here and repeat this cycle a couple of times before I say, okay, and now done. Is this perfect? No, of course not. This is some protection, but of course it's not perfect in the development, because you can kind of feel that the more you go back here, at some point also this validation set will be overutilized. So it's not like this is a full protection, but at least I'm already not utilizing my test set to do that, right? Now, then the question is, okay, what's the best scheme in terms of validation that I can think of that allows me to both maybe try out a couple of things or compare a couple of different configurations that avoids me to come across a lucky hit that just seems to work for this particular train test split, right? And that would also allow me to go back a couple of times. So maybe one aspect will be, okay, every time you go back, resample your train and validation set, right? That at least brings in a bit more variety so that you're not always using the exact same train and validation split. What else can we do? Well, maybe there is a particular model configuration that tends to work on this exact split, but maybe overall, if you would repeat the experiment a couple of times, would not be the best configuration anymore. So let's try to make that a little bit more robust, that setup. And that's why you do cross-validation, right? And you replace this simple split approach with a cross-validation approach. And then you say, okay, you have your train data, right? You split it into n cuts or faults, and we basically train not one version of our model using a particular configuration, but we train our model 3 times. Once using split 1 and 2, once using split 1 and 3, and once using split 2 and 3. So we always leave out one fault, and we utilize that fault to do a validation evaluation there. And then, of course, you will not get one metric here. You will get 3 values for your AUC, but then typically you average them together. So this is what you get. So these are AUC values, 75%, 71%, 84%. This already reveals why it's nice to do this a couple of times, because this seems to be a good evaluation metric, but just simply for this particular lucky hit that we had, averaged, it's not so high as we thought it would have been. So that's already a benefit of not just using one split, but maybe creating a couple of splits. This is for one particular model configuration, as I call it. Not just meaning one particular type of supervised learning algorithm, but even a specific configuration of its hyperparameters as well, right? Meaning that even if you would just be training something like a logistic regression and you plan to use rich regularization, that this would be your situation, that for every value of this alpha, or lambda as we called it for rich, right, that you run it 3 times over the 3 faults, you calculate the 3 evaluation metrics, and you average them. And from there, the goal is that through this cross-validation, you select what is your best configuration that you can find over here, until you're again ready to take that best configuration and bring that forward as your final model to test out on the test set. Now, question, what is the final model following from this kind of comparison? Because for every configuration, you basically construct or train the model 1, 2, 3 times in this case. So what is your best model? Well, there you have choices, right? So here it follows that across all my configurations, this one is the best because it gave me the best average performance metric over this cross-validation run that I did here. What is then my best model? Either I take the one that internally led to the best result, or I say take this configuration and then retrain the model one more time using the full training data and bring that one forward to your test set. That's also sometimes done, especially if you do not have a lot of training data. Now, most implementations, of course, make that pretty easy and do that automatically, but that's exactly like if you see this output, for instance, it tries out different values for alpha, lambda, and these are the averaged metric scores, and it selects the best one here based on the best RMSE value, which turns out to be 10% for lambda and 33% for alpha and 33% for lambda. Okay, that's all fine and good. Now, is this perfect? No. I mean, if you always work with the same piece of training data, yes, you cut it up into pieces, but also here, if you continue to do this forever and forever and forever, there is some overfitting going on here, right? We only try to use this to avoid us from overfitting too quickly, but that's also the reason why we still need a test set at the end, because you could continue to play this game until there is a configuration that leads to acceptable performance results. But maybe by then you have already completely screwed up your approach, or you have been featureizing in a way which is not clean or whatever. So even if you apply cross-validation, there is still this test set that you utilize. This helps you to perform model tuning and selection. This helps you to evaluate, right? Hence why these are different concerns. So a way to protect against overfitting and ensuring validation by adding diversity in repeated runs to prevent lucky hits. And of course, here there is also different types that exist. For instance, for time series, you cannot just take out samples from the middle of the time series, because then for any model it would be easy to interpolate. So just as the way how you need to think about how you set up your train and test split, you would follow the same approaches or concerns for your validation faults in cross-validation as well. Now, for a test set, it's typically the case that we try to perform it in such a way that it's out of time by default. When cutting up a train set of data into faults, the only reason why the time aspect is really important is typically when you work with time series related data. Otherwise, it's fine to do it just randomly. Another thing that you sometimes need to take into account is whether you should be wary of grouping effects when setting up your cross-validation run. And I will give you an example of something that happened in real life. It's a use case where people had developed a deep learning model to look at radiology scans of lungs during COVID, right? And what they had done is they had constructed a trained set of data, and I don't even think they utilized, but that's pretty common sadly in deep learning. People tend to forget about the necessity of a true test set, so they didn't really even collect a test set from a different point in time, in which case they might have spotted their mistake sooner, and they in fact had to retract the paper and make some changes. So they just had one collection of data, and they decided to use cross-validation not just as a way to tune their models, but also to get an idea on the generalization performance. So they were also using cross-validation as an evaluation kind of aspect in this case as well, which is not always wrong, but again, in deep learning they have that tendency, and I'm heavily against it. I even think that also there you should work with a true test set instead, but whatever. What they had done is they had just split up all of the images that they had randomly across a set of faults. Or I think in the case, because it was a deep learning model, probably it was just one split that they had made, and they just kept a piece as training data and a piece as validation data. But what they had forget, but the same applies if you would be using cross-validation, so that's the same thing. But what they had to forget to take into account is that these images were collected from labs across a couple of hospitals. Is it, of course, you might have effects such as, and I don't think it was patients in this case, but it had to do with type of machines. So certain labs tend to buy certain equipment, and before images are exported, the software that they use or the machine that they use tends to place certain markers on images. Small logos of the device that made the image, or small textual information, or maybe an identifier of the hospital where the image was taken. So lots of like extra information on an image. So what they had is they had a bunch of images, but they were grouped because some of the images shared pieces of information that all made them belong to the same hospital, Hospital 1 and Hospital 2 and so on. And then they randomly just distributed these across train and validation set. And it seemed that the model was doing a great job on the validation set. Nicely random split. But under the hood, what the model had actually learned to do is not really look at the contents of the lungs that were in the image, but it was paying more attention to these markers that were on the images, because it had learned to figure out, especially in the early days of COVID, there were some hospitals that very quickly got overworked or got a lot of cases. So they had way more COVID cases than other hospitals. And by looking at this identifiable information about which machine is it, which hospital is it basically had learned to find an association, a correlation between, it's this hospital, more likely to be a COVID case of a lung in that sense. Same for markers that identified the type of machinery that was being utilized. I mean, imagine if you have a patient coming from an ambulance entering your hospital, the choice of which machine to utilize will probably be related to the severity of the case. And indeed, that's what happens. Hospitals have machines where you need to go lie down and you need to be still. They also have portable mobile scanning machines. If you're very sick and you can barely sit up, they utilize the portable mobile versions of the machines. What did the model see? Mobile version of the machine, you'll probably have COVID, right? Same, if you use cross-validation and there is this grouping effect going on, make sure that you split according to these groups. So what they should have done is they should have put a group of hospitals into the train data and a separate group of hospitals into the validation data. Likewise, if you do cross-validation, keep that aspect into mind as well. Yeah, leave one out cross-validation is an extreme form where you have as many faults as you have instances. So you only utilize a single instance to evaluate your model on. And sometimes you will hear, of course, that's a lot of work because you're training as many models then as you have instances, so it takes very long. But sometimes you will hear the claim being, which is a correct claim, but the argument for it that you will sometimes hear being mentioned is, but this is the only way how you can get an unbiased error estimate when you're using cross-validation. So meaning if you would like to get a true estimate of the model, right, in terms of that error score that you get, it's best to have as many models as you have instances -1, or instances, except leaving always one out, and then averaging those. That's true, except that there, what we forget about, so as it mentioned here, the problem with cross-validation is that it gives a pessimistically biased estimate of performance because most statistical models will improve if the training set is made larger. So hence the reason why only leaving one instance out, because then you make it as large as you can. That's true for simple statistical models, and biased here is not really related to, we get wrong scores or the end result would be worse. Bias here is related to the two sources of model error that you can deal with. One being bias, which is related to your model being a quite simple model, and the other one being related to variance, which is related to the degree of overfitting that's going on by your model. And so people, or especially when you use a very simple model like a linear regression or something like that, or a logistic regression, people will tell you, you're better off using leave one out cross-validation, because that is approximately unbiased, because the difference in size between your training set used in each fault and your entire training data set is only a single pattern, meaning that the models that you build, especially for models that are not very complex already, that if you reduce the size of your data set, you will introduce your more bias as a source of error, right? And they will end up performing less well, right? Which is true. However, in today's cases, where you have a lot of data to begin with, right? You don't have 30 instances, you have a lot of data to begin with, and where you're using models that have a strong degree of complexity already, our issue is not so much that we're afraid of making our models dumber, right? Because them being too simple already, or us not having enough data and adding more sources of bias. Nowadays, we're more concerned of having more error coming from variance, right? Of models being overfitting instead. So rather than going for leave one out cross-validation because you're afraid, the more data, the better, and if I do normal cross-validation, I'm not giving them enough data, make sure that you have enough data, right? And secondly, you're mainly trying to prevent your models from overfitting, and you're trying to safeguard generalization capability. So the reasoning behind this is correct, but in most real-life cases where you use like solid complex models and you have a lot of data, utilize normal cross-validation with a couple of faults, right? Do not use this extreme form of leave one out cross-validation. It's also not worth it because you will spend way too much time training that whole bunch of models anyway, right? So that's not worth it. Couple of additional notes to close off evaluation. Multi-class, yeah, what about that? First of all, I hope that you can see that the confusion matrix stays more or less the same. You're just contrasting the different classes with one another. Important to look at it, like what this already shows is what are the classes that get most confused with one another. These are two different breeds of dogs. No wonder that they look quite similar to my model. Again, try to inspect whether this is logical to you or not. You can calculate ROC curves, but it's a bit harder. What you basically do is when you have three classes, you just make three different curves for each class separately, where you each time pretend basically that that specific class, class 0, class 1, class 2, is the positive class, and the other two are the negative classes, and you just calculate your curves accordingly. Of course, then you have three curves. If you then want to have a single curve, you need to take like the average in some way of those three curves. And then you can either calculate the micro average or you can calculate the macro average. One just looks at what are the three curves and we just have them count for the same amount. So all of these values count for 1/3. The other type weights it based on the number of instances that belong to that class. So that's the difference between micro and macro averaging. But you can then calculate some sort of average curve, and then you can calculate an AUC value there as well. But you also have different metrics for multi-class as well. You can look them up. So those exist too, but this is quite common as well. Also, but this is not oftentimes the case anymore, but like some ideas of what if you can only do binary classification. For support vector machines, this was commonly the case. Well, then you try to transform your multi-class approach to a binary approach, either trying to do a 1 versus all setup or a 1 versus 1 setup. So this is 1 versus all. Basically means that for you build as many classifiers as you have classes. So here I have A, B, and C. And same thing as with these ROC curves over here. I always pretend that one class is the positive and the two other classes are the negative. And I just build a model like this, like this, like this. And then if I need to score a new instance, I just let my three models vote on that. This one says A versus not A, B versus not B, C versus not B. The result would be A here because it gets the highest probability value. This is 1 versus 1. Here you build pairwise combinations of contrasting. So here I try to decide are you A or are you B, but I ignore the C's. Here I'm trying to decide are you A or C, but I ignore the B's. And here I try to decide are you B or C, but I ignore the A's. Again, if a new case comes along, I let each models vote, and I just here do it based on majority voting. A wins, right? 2 out of 3, so my end result would be A. You can even then try to extract some probability based on the number of models that vote A, but you're only going to get 33, 63, 100% here, or 0% for any of your classes, so that's maybe less useful. Multi-label here too, if you do not have a lot of possible labels, so difference multi-class means it's one of possible outcomes. Multi-label means it can even be more than one class or label that an instance has. Then you can say, well, the easiest way is just to independently train a binary classifier for each of the labels that I have. And they all get ran if a new instance comes along. And that is what I decide that you will have in terms of labels. But this, of course, then like we also said a couple of weeks ago, then you kind of miss the relationship that potentially exists between the different labels that you have. If you need to predict whether an image contains a mouse, a dog, a cat, and it can be all three of them or two of them or none of them, of course, if there is a mouse in the image, it's probably less likely that there is a cat in the image, right? So if you build all of these three separately, you kind of miss these underlying links between the targets, you miss those correlations. So then you can apply something like classifier chaining, where you first build a first model that predicts whether there is a mouse, but then you use the prediction of that model as a feature in the next model that you're going to build. That's called classifier chaining. Or you could also try to set up a multi-class problem, where you go over all the possible combinations that might arise, and you try to then take it as a multi-class problem. But then again, this being not very balanced is more likely, and this leads to an explosion of combinations that you will have if you have like more than 3 classes, as is the case here. Then this becomes intractable to convert into a multi-class problem, which is also a reason or a setting where typically artificial neural network-based approaches would give you a better result in these cases than the more standard or traditional techniques would be able to give you. I already mentioned this, if your final evaluation, even if you set up this correctly, this comes out of time. What if this result is way worse than what you got over here? Yeah, let me go back and try something else. You can, but you do know that with every repetition of this cycle, you are kind of abusing your test set further and further. So ideally, you would have to find a new test set. That's of course not always easy in every setting. So yeah, throw away the whole project, probably not, but it's not bad that this happens. I mean, we are only human, but do note that the more that you revisit that same test set, the less of a meaningful role it can actually play for your project. So that's definitely the case. Already mentioned every transformation, learn it on the train data. Other things I think already discussed enough as well. Do try to use a test set. Cross-validation as a replacement for an evaluation is not really a good idea, so try to avoid that as well. And if you ever see AUC scores that look too good to be true, like close to 100, they probably are. Maybe you have some data leakage going on as well. So always try to be a bit mindful of that too, right? Now, what if you have very little data? So those are some extreme situations in which you can say, okay, hopefully you have more instances than features. Otherwise, yeah, good luck. But let's say you do not have a lot of instances, so you're really not for the idea of making a separate test set. And moreover, you're really not for the idea of using a cross-validation with 2 or 3 faults. You really would like to use leave one out cross-validation because you are running into too few data elements available problem. In that case, sure. In that case, you can utilize cross-validation and even leave one out cross-validation, and also utilize the evaluation metrics that reports as your final evaluation metric, let's say, to kind of assess, well, my model is doing this well, and this result came from a cross-validation. You can do that, but then obviously, please do not test out 5,000 configurations in that cross-validation and saying, well, this is the best one. Try to limit your choices in terms of model selection. And preferably, that's a setting where you would do feature selection first or stick to quite simple models as well. So very often, and even papers do this sometimes, that they will report the quality of their models and use cross-validation for that. You can, but it's better to really utilize a completely new fetched test set from a different period in time even. Option 2 is fit on the, that's even worse, fit on the training data only and report some degree of fit or goodness of fit. But then, of course, you know that you should limit yourself to parametric models. Not use KNN with k equal 1, right? It's going to look great on your train data, but it won't really be, right? So in most cases of machine learning, the true answer here is if you have very little data available, be wary of using machine learning. Maybe look at other types of analyses that can help you out, right? If you have 20 instances, I mean, nothing's going to work, right? What about unsupervised models? We didn't talk about these ones in depth yet, but we saw them in the introductory session. Yeah, there you also have evaluation metrics that exist, but they're a bit more subjective because, yeah, you can contrast a clustering solution to kind of some true values, but then in a way you're setting it up as a supervised learner, actually. What does it mean for a clustering solution to be good, right? That depends, separability, distance, but maybe for you it means other things, so it will always be a little bit more subjective in the case of unsupervised models. Test sets, also less common, because typically unsupervised techniques, they're either utilized as some kind of descriptive purpose approach, and then we don't really care about generalization because it's descriptive. And if we do utilize them in a predictive pipeline, they are embedded in the rest of that pipeline, and then indeed there will be a train and test split, and we will see how well that works as a featureization approach in most cases when executing it on a test set. So just using an unsupervised technique on its own, quite rare that you will then utilize a test set, for instance, to say, I did k-means on this piece of data, but now tomorrow I have new instances, and if I would assign them to the centroids that I found last month ago, how good would these assignments then still be? Less of an important question, except when you're using those k-mean centroid distances as a feature in a downstream predictive model that you're building. If it's just the clustering that you're doing, you might just as well say, no, every month we can do the clustering again, done, right? Because then it's more descriptive rather than predictive in nature. Calibration methods I already spoke about a little bit when talking about the oversampling and downsampling. Generally speaking, there exists, just so that you know about this, but there exists approaches for models that are not well calibrated to kind of take their probability output that they give you, or output distribution, and recalibrating it so it's closer to something that you would expect from, let's say, logistic regression. Like next time we will look at random forests, and there you will see that they have difficulty of making predictions that are close to 0 and 1, for instance. So here, for instance, if we look at random forest, but also in the case of a support vector machine even, you see that kind of the distribution that they're giving me, or here for random forest, kind of looks a bit weird with these two bumps, but it doesn't like to go to 0, it doesn't like to go to 1, so maybe we can recalibrate that to be more in line with the blue or dark blue curve or distribution that logistic regression is giving me. And in some cases that can be important, like if you're thinking about ranking instances even, the fact that your probabilities do not start with 1, it's already a little bit strange. But secondly, also, like if you would be utilizing or playing in a competition and you would be evaluated on something like RMSE or something like categorical cross entropy, rather in the case of binary classification, but your classifier does not like to predict 0 or 1 as a probability, you already lose some loss in that case. So also then you can consider utilizing a calibration approach to fix this. Okay, that's basically to close with these slides. We will come back to them when we discuss more about tooling, but what they basically try to convey is that your evaluation of your model does not stop after you have evaluated your model on your test set. Also, when putting your model into production, you need to continue to monitor it and eventually keep it under maintenance, right? Because time will go forward, things will change. At some point, every predictive model breaks down. So this is what I discussed before, like typically you monitor distributions of your input data, you check if you do not have new categorical levels that appear or new missing values that appear. You can use metrics such as the system stability index that tell you how close is your sample of data that you take today to the training data that you utilized to train your model. If that becomes too far straight away, right, or too far off from the train data that you utilized, you should perhaps retrain your model. Output predictions, same. From time, take samples and maybe not just always take the top 100 cases that your model predicts, but also spot check some other cases as well to see if it's also still doing well there and it's not missing cases, and check whether the distribution of predicted probabilities is the same as the distribution that you observed back when you trained your model. So likewise there. Which performance metrics to utilize? Like I already mentioned, sometimes it's not just the probability or AUC, but trying to bring in monetary aspects in there as well, maybe likelihood and mixing that versus consequences or damage or value. I think I already mentioned that as well. Making sure, again, if this is where you trained your model for, and tomorrow you have a case which is all the way over here, if you do not have any monitoring in place that warns you about this, your model will just happily or as happily make a prediction for a case over here as a case over there, right? So that's why you typically also need monitoring solutions after deploying your model that can warn you for this. There are a couple of nice papers that go into more detail. The Googlers or the Google people have done a lot of work on this about hidden technical debt, as they call it, or ways to quantify, like, okay, how far away is my data today from my training data, or there are metrics that exist for that. You can kind of, they're pretty old papers, but they're still very valuable to kind of give solutions or advice to kind of monitor systems. This is a screenshot from that paper. And then to close with, and I've been saying this for a long time, but what you do see is that nowadays, but we'll come back to data science platforms later as well, that it used to be that if you bought tooling as a data scientist, that it was heavily oriented towards you as a developer, you setting up maybe a run with 500 different versions of your model and doing a hyperparameter tuning and contrasting which one is the best, towards now more platforms that go more to the deployment aspect of this process, where really most of the mistakes can happen, if you're honest. Like just keeping a model running but not checking it is kind of a recipe for failure. So there are a couple of companies that have entered this space and are also now offering tooling